Picture a region of space so extreme, so hostile, that light itself struggles to escape its grasp. Now, imagine another star, still burning bright, slowly being devoured by its voracious partner, all while sending out a steady scream of high-energy X-rays into the cosmos. These aren't scenes from a science fiction movie. They're happening right now, in countless systems scattered across our galaxy and beyond. These are X-ray binaries, some of the most mind-bending phenomena in the universe. What makes these systems so fascinating isn't just their raw power, though that's definitely part of it. It's what they tell us about the extremes of physics and the life cycles of stars. X-ray binaries are systems where a dense, compact object, usually a black hole or a neutron star, feeds on material from a nearby companion star. As this stolen matter spirals inward, it heats up to millions of degrees, releasing torrents of X-rays that we can detect across unimaginable distances. But why does this happen? How does a system like this form in the first place? And what can these violent interactions reveal about the nature of space, time, and gravity itself? Let's start with the basics. To understand X-ray binaries, you first need to grasp the concept of stellar evolution, the life and death of stars. Stars don't live forever. After spending millions or even billions of years fusing hydrogen into helium in their cores, they eventually run out of fuel. What happens next depends on the star's mass. Smaller stars, like our Sun, swell into red giants before shedding their outer layers and settling down as white dwarfs. But for more massive stars, the endgame is far more dramatic. When a star several times the mass of the Sun exhausts its nuclear fuel, it can no longer resist the pull of gravity. The core collapses, triggering a supernova explosion that blasts the outer layers into space. What's left behind is either a neutron star, a ball of ultra-dense matter, or, if the original star was massive enough, a black hole. Now, here's where things get interesting. If this massive star happened to have a companion, a second star orbiting nearby, its violent death could pull the companion into a very different kind of relationship. Over time, the compact remnant, whether it's a neutron star or a black hole, might start stealing material from its partner. This process, called accretion, is what powers the intense X-ray emissions we see in these systems. But not all X-ray binaries are the same. They fall into two broad categories: low-mass X-ray binaries, LMXBs, and high-mass X-ray binaries, HMXBs, depending on the mass of the companion star. In LMXBs, the donor star is usually smaller and cooler, something like a Sun-like star or even a white dwarf. These systems often involve a slow, steady transfer of material. HMXBs, on the other hand, feature massive, hot, and young stars, and the material transfer is often chaotic, driven by powerful stellar winds. Let's zoom in on what happens during accretion. When material from the companion star gets close to the compact object, it doesn't just fall straight in. Instead, it forms a swirling disk around the neutron star or black hole. This disk, called an accretion disk, is a cauldron of extreme physics. Friction and gravitational forces heat the gas in the disk to temperatures so high that it glows in X-rays. The closer you get to the compact object, the hotter and more energetic the emissions become. And if the compact object is a black hole, the innermost regions of the disk may even get close to the event horizon, the point of no return, where space and time warp in ways we can barely comprehend. In some systems, particularly those with neutron stars, things get even weirder. Neutron stars often have strong magnetic fields, which can channel the inflowing gas onto the star's magnetic poles. This creates hotspots that pulse as the neutron star spins, producing regular bursts of X-rays. These systems, called X-ray pulsars, are like cosmic lighthouses, beaming their high-energy signals out into the void. But X-ray binaries aren't just fascinating for what they are, they're also incredibly useful tools for astronomers. By studying the X-rays they emit, scientists can learn a ton about the physics of accretion, the behavior of matter under extreme conditions, and even the properties of the compact objects themselves. For example, the way X-rays vary over time can reveal the size and structure of the accretion disk, while the energy spectrum of the X-rays can tell us about the temperature and composition of the gas. One of the most exciting aspects of X-ray binaries is what they can teach us about black holes. Black holes are notoriously hard to study because they don't emit any light of their own. But in an X-ray binary, the accretion disk acts as a kind of spotlight, illuminating the black hole's presence and allowing us to measure its mass and spin. These measurements are crucial for testing theories of gravity and understanding how black holes grow over time. And then there are the mysteries. For all we've learned about X-ray binaries, there's still so much we don't understand. Why do some systems produce powerful jets of particles that shoot out at nearly the speed of light, while others don't? How do magnetic fields influence the behavior of the accretion disk? And what happens in the final moments before material crosses the event horizon of a black hole? These questions aren't just academic. They're tied to some of the biggest mysteries in astrophysics, including the nature of dark matter and dark energy, the origins of gravitational waves, and the ultimate fate of the universe itself. X-ray binaries are like natural laboratories, giving us a front-row seat to some of the most extreme environments in existence. And the best part? We're just scratching the surface. New telescopes and space missions are being designed to probe these systems in unprecedented detail, from the European Space Agency's Athena X-ray Observatory to NASA's proposed Lynx mission. These instruments will allow us to map the X-ray sky with greater precision than ever before, uncovering new systems and shedding light on old puzzles. X-ray binaries remind us of something profound. The universe is full of hidden dramas playing out far beyond the reach of our eyes. They're a testament to the power of science to reveal the invisible, to make the unknowable just a little bit more comprehensible. And they're a reminder that even in the darkest corners of space, there's light, if you know where to look. The story of X-ray binaries doesn't stop at what we can see with current instruments. It delves into the very fabric of our understanding of physics. One of the most compelling reasons these systems captivate scientists is their ability to challenge and expand the boundaries of established theories. For instance, the interaction between matter and gravity in these systems gives us a real-world testbed for Einstein's general theory of relativity. When matter spirals into a neutron star or black hole, the extreme curvature of spacetime distorts the paths of particles, producing phenomena that can be observed and compared against theoretical predictions. Take, for example, the concept of relativistic jets. These are powerful streams of particles ejected from the vicinity of a compact object, often at speeds approaching the speed of light. While the mechanics of their formation remain an active area of research, it's believed that the magnetic fields near the accretion disk play a critical role. These jets are not only fascinating on their own but also provide a way to study the environment around black holes and neutron stars. By analyzing the composition, speed, and direction of these jets, astronomers can gather insights into the magnetic and gravitational forces at play. Another intriguing aspect of X-ray binaries is the behavior of their accretion disks. These disks are far from simple structures. They're dynamic, turbulent, and full of surprises. In some systems, the disk undergoes sudden changes, leading to dramatic fluctuations in X-ray brightness. These outbursts are thought to be caused by instabilities in the flow of matter through the disk. Understanding these phenomena requires not just observational data but also complex computer simulations that model the physics of accretion in detail. Even more fascinating are the periodic signals that emerge from certain neutron star systems, known as quasi-periodic oscillations (QPOs). These are variations in the X-ray intensity that occur at nearly regular intervals, hinting at the underlying processes in the accretion disk or the neutron star's magnetic field. QPOs are like fingerprints of the extreme physics happening in these systems, offering clues about their structure and dynamics. Then there's the question of spin. Both neutron stars and black holes in X-ray binaries often rotate at incredible speeds, a legacy of their formation during the collapse of a massive star. The spin of these compact objects can have a profound effect on the behavior of the surrounding accretion disk. For black holes, the spin determines how close the disk can get to the event horizon. A rapidly spinning black hole drags spacetime around with it, a phenomenon known as frame dragging, allowing the disk to extend closer and emit higher energy X-rays. By measuring the X-ray spectrum, astronomers can estimate the spin of a black hole, unlocking yet another piece of the puzzle. Neutron stars bring their own set of complexities. These objects are essentially giant atomic nuclei, with densities so high that a single teaspoon of neutron star material would weigh billions of tons. They are also incredibly magnetic, with fields millions or even billions of times stronger than anything we can create on Earth. This magnetic power can influence the way matter is accreted, creating hotspots that pulse as the neutron star rotates. The interplay between the star's rotation, magnetic field, and the infalling matter creates some of the most intricate and challenging physics known to science. But perhaps the most mysterious aspect of X-ray binaries is the transition some systems undergo from being relatively quiet to becoming active X-ray sources. Known as transient X-ray binaries, these systems spend most of their time in a dormant state, emitting little to no X-rays. Then, seemingly out of nowhere, they burst into activity, with the accretion disk suddenly flaring up and releasing enormous amounts of energy. These transitions are thought to be triggered by changes in the flow of material from the companion star, but the exact mechanisms are still not fully understood. Why do some systems remain stable while others erupt? What triggers these sudden bursts of activity? These are the kinds of questions that keep astronomers awake at night. Another area of intense study is the role X-ray binaries play in the evolution of galaxies. While they may seem like isolated systems, their high-energy emissions can have far-reaching effects. The X-rays produced by these systems can ionize the surrounding gas, influencing star formation and the chemical evolution of their host galaxies. This connection between the microscopic, tiny, dense objects in close orbit, and the macroscopic, the behavior of entire galaxies, is a perfect example of how interconnected the universe truly is. And let's not forget the role X-ray binaries play in the search for gravitational waves. When two compact objects, such as a neutron star and a black hole, orbit each other closely, they lose energy in the form of gravitational waves, ripples in the fabric of space-time first predicted by Einstein and detected for the first time in 2015. X-ray binaries, especially those containing two compact objects, are prime candidates for studying this phenomenon. By observing these systems, astronomers can refine their models of how gravitational waves are produced, opening up new ways to study the universe. What's truly humbling about all this is how much we still don't know. X-ray binaries are incredibly challenging to study because their most interesting features, accretion disks, jets, and the compact objects themselves, are often hidden from direct view. Much of what we know comes from interpreting the X-rays they emit, but these signals can be complex and difficult to decode. Advances in technology, from more sensitive X-ray detectors to more powerful telescopes, are constantly pushing the boundaries of what we can learn. Missions like Chandra, Newton, and NICER have already provided a wealth of data, but the next generation of observatories promises to reveal even more. In many ways, X-ray binaries are the ultimate cosmic laboratories. They take us to the edge of what's possible in physics, showing us the extremes of gravity, density, and energy. They force us to question our assumptions and refine our theories, offering a glimpse into a universe that's far stranger and more complex than we ever imagined. And as we continue to study these systems, we're not just learning about the stars, they're teaching us about ourselves, about our place in the cosmos, and about the limits of human understanding. X-ray binaries also serve as a vital bridge between theoretical physics and observational astronomy. They offer an extraordinary opportunity to validate the theories of quantum mechanics, general relativity, and magnetohydrodynamics under conditions that are impossible to replicate on Earth. Each new discovery in these systems tends to raise more questions than answers, providing a never-ending loop of scientific curiosity and exploration. For instance, consider the fascinating relationship between mass transfer and the long-term evolution of X-ray binaries. When the companion star donates material to the compact object, it loses mass, altering the dynamics of the binary system. This process can significantly affect the companion star's structure and lifespan. Some companion stars in X-ray binaries have been stripped down to their cores, revealing new insights into stellar evolution. Furthermore, the amount and rate of accreted matter can influence the rotation of the neutron star or black hole, potentially spinning them up to near their theoretical speed limits. The rapid rotation of these compact objects often leads to extreme physical phenomena. For neutron stars, this can result in the formation of millisecond pulsars, spinning neutron stars that emit precise beams of radiation. These pulsars are not only fascinating objects in their own right but also serve as natural laboratories for studying the fundamental properties of matter under extreme pressures and densities. By studying the pulses emitted by these stars, astronomers can probe the composition and behavior of matter at nuclear densities, something that has implications for fields ranging from particle physics to cosmology. When it comes to black holes, spin takes on a particularly intriguing role. The spin of a black hole not only determines the extent of frame dragging effects but also plays a critical role in powering relativistic jets. These jets, which can extend for thousands or even millions of light years, are among the most energetic phenomena in the universe. Despite their immense power and scale, the exact mechanisms driving these jets remain one of the great unsolved mysteries of astrophysics. What is clear, however, is that they are intimately tied to the black hole's spin and the magnetic fields in its vicinity. The accretion disks in X-ray binaries are another source of wonder and complexity. These disks aren't static or uniform. They are constantly shifting, evolving, and reacting to changes in their environment. In some cases, the accretion disk becomes unstable, leading to the formation of spiral waves or other structures. These instabilities can have profound effects on the emission of X-rays, creating patterns that astronomers can study to learn more about the inner workings of these systems. One particularly interesting feature of accretion disks is their temperature distribution. The inner regions of the disk, which are closest to the compact object, are incredibly hot, reaching millions of degrees. This is where the X-rays are primarily emitted. Further out, the disk becomes cooler, emitting light at optical or infrared wavelengths. By studying the emission across these different wavelengths, astronomers can piece together a detailed picture of the disk's structure and behavior. Magnetic fields also play a crucial role in shaping the behavior of X-ray binaries. In systems with neutron stars, the magnetic field can funnel in falling material toward the star's magnetic poles, creating hotspots that emit X-rays. These hotspots rotate with the neutron star, producing pulsations that can be observed from Earth. The strength and configuration of the magnetic field can vary widely between systems, leading to a diverse range of behaviors and observational signatures. Some of the most extreme X-ray binaries are those containing black holes or neutron stars that are actively pulling in large amounts of matter from their companion stars. These systems can emit X-rays at rates that rival or exceed the combined luminosity of entire galaxies. Known as ultraluminous X-ray sources, ULXs, these systems challenge our understanding of accretion physics. While some ULXs are thought to contain intermediate mass black holes, others appear to host neutron stars, raising questions about how these relatively small objects can sustain such high levels of energy output. Another fascinating subset of X-ray binaries are the so-called microquasars. These systems, which typically involve a stellar mass black hole and a companion star, exhibit properties similar to those of quasars, which are powered by supermassive black holes. Like quasars, microquasars produce relativistic jets and show complex variability in their emissions. By studying microquasars, astronomers can gain insights into the processes that occur near black holes of all sizes, from stellar mass to supermassive. But the significance of X-ray binaries extends beyond their immediate environments. These systems can have far-reaching effects on their surroundings, influencing the interstellar medium and even the evolution of their host galaxies. The X-rays emitted by these systems can heat the surrounding gas, affecting the conditions for star formation. Over long timescales, the energy and material released by X-ray binaries can shape the chemical composition and structure of their host galaxies, making them key players in the cosmic ecosystem. Moreover, X-ray binaries are invaluable tools for studying populations of compact objects in different types of galaxies. By comparing the properties of X-ray binaries in spiral, elliptical, and irregular galaxies, astronomers can learn about the factors that influence their formation and evolution. This, in turn, provides clues about the history and dynamics of galaxies themselves. One of the most tantalizing prospects in the study of X-ray binaries is the potential to detect new types of compact objects. While neutron stars and black holes are well established as the remnants of massive stars, there is ongoing speculation about the existence of exotic objects such as quark stars or boson stars. These hypothetical objects would have properties distinct from those of neutron stars or black holes, and X-ray binaries could provide a unique setting for discovering them. X-ray binaries remind us of the interconnectedness of the universe. These seemingly isolated systems are tied to some of the most fundamental processes in astrophysics, from star formation and stellar evolution to the behavior of matter under extreme conditions. They challenge us to think beyond our everyday experiences and consider the extraordinary forces and phenomena that govern the cosmos. And yet, for all their complexity and intrigue, X-ray binaries remain fundamentally mysterious. Each new observation adds another piece to the puzzle, but the complete picture is still far from clear. What's certain is that these systems will continue to captivate astronomers and the public alike, offering endless opportunities for discovery and wonder. The study of X-ray binaries is not only a journey into the extreme conditions of the universe but also a testament to humanity's ingenuity in unraveling the mysteries of the cosmos. Every step forward in understanding these systems brings us closer to answering some of the biggest questions in astrophysics, while simultaneously opening doors to new and unexpected avenues of inquiry. One of the most compelling aspects of X-ray binaries is their role as natural laboratories for testing the limits of physical laws. For example, the immense gravitational fields of black holes and neutron stars allow us to study the effects of general relativity in extreme environments. Frame dragging, gravitational redshift, and event horizon behavior are just a few phenomena that can be explored through these systems. Observations of X-ray binaries have already provided key insights into the nature of spacetime, and ongoing research promises to deepen our understanding even further. Moreover, these systems offer a unique opportunity to study the interplay between gravity and electromagnetic forces. The intense magnetic fields associated with neutron stars, in particular, create environments where plasma physics and magnetohydrodynamics can be studied in ways that are impossible to replicate on Earth. The interactions between these forces often result in highly dynamic and unpredictable behavior, including the formation of accretion-driven winds, disk instabilities, and the ejection of relativistic jets. Relativistic jets, in particular, are a fascinating phenomenon observed in many X-ray binaries. These jets are composed of charged particles that are accelerated to nearly the speed of light and are often accompanied by powerful electromagnetic radiation. The mechanisms that produce these jets remain an area of active research, but they are believed to involve a combination of magnetic field interactions and the rotational energy of the compact object. By studying the properties of these jets, astronomers can gain insights into the processes that drive them and their impact on the surrounding environment. For instance, jets can carry significant amounts of energy away from the binary system, influencing the interstellar medium and even the host galaxy. These outflows can heat the surrounding gas, suppressing or triggering star formation, depending on the local conditions. In some cases, the material ejected by jets can form shock waves that accelerate cosmic rays, contributing to the high-energy phenomena observed in the universe. Understanding these processes is crucial for developing a comprehensive picture of how X-ray binaries interact with and shape their cosmic neighborhoods. Another intriguing aspect of X-ray binaries is their variability. These systems are highly dynamic, with changes in brightness and spectral properties occurring over a wide range of timescales. Some of these variations are driven by changes in the accretion flow, such as disk instabilities or fluctuations in the rate of mass transfer from the companion star. Others are caused by geometric effects, such as the eclipsing of the X-ray source by the companion star or the precession of the accretion disk. This variability provides a wealth of information about the inner workings of X-ray binaries. For example, quasi-periodic oscillations (QPOs) observed in the X-ray emission of some systems are thought to arise from the interaction between the accretion disk and the compact object's magnetic field or from oscillations within the disk itself. By analyzing these oscillations, astronomers can probe the structure and dynamics of the accretion disk, as well as the properties of the compact object. Even more dramatic are the outbursts observed in some X-ray binaries. These events, which can last for days, weeks, or even months, are thought to result from sudden increases in the rate of mass transfer or instabilities in the accretion disk. During an outburst, the system's X-ray luminosity can increase by several orders of magnitude, providing a rare opportunity to observe the accretion process in action. The study of outbursts has led to significant advances in our understanding of how matter flows onto compact objects and how energy is released in the process. In addition to variability, X-ray binaries exhibit a wide range of spectral properties that provide clues about the physical conditions in these systems. By analyzing the X-ray spectra of these systems, astronomers can determine the temperature, density, and composition of the accreting material, as well as the properties of the compact object. For example, the presence of certain emission lines in the spectrum can indicate the presence of heavy elements such as iron, which are often produced in supernovae and recycled into the accretion disk. The detection of these spectral features is made possible by advances in X-ray astronomy, including the development of space-based observatories such as Chandra, Newton, and NuSTAR. These telescopes are equipped with sensitive detectors that can capture high-resolution X-ray spectra, enabling astronomers to study X-ray binaries in unprecedented detail. The data collected by these observatories have not only expanded our understanding of X-ray binaries but also highlighted the need for new and more powerful instruments to continue the exploration. In recent years, the field of X-ray binary research has been revolutionized by the advent of multi-wavelength and multi-messenger astronomy. By combining observations across the electromagnetic spectrum, from radio waves to gamma rays, astronomers can obtain a more complete picture of these systems. For example, radio observations of relativistic jets can provide information about their structure and motion, while optical and infrared observations can reveal details about the companion star and the outer regions of the accretion disk. The detection of gravitational waves from merging neutron stars and black holes has added an entirely new dimension to the study of X-ray binaries. While most X-ray binaries are not currently detectable sources of gravitational waves, future advancements in gravitational wave astronomy may allow us to identify binary systems that are on the verge of merging. These observations could provide new insights into the final stages of binary evolution and the formation of compact object mergers. As technology continues to advance, the future of X-ray binary research looks brighter than ever. New telescopes and observatories, such as the James Webb Space Telescope, JWST, and the upcoming Lynx X-ray Observatory, promise to push the boundaries of what we can observe and understand. These instruments will allow astronomers to study X-ray binaries in greater detail, uncovering new phenomena and refining existing models. Yet, for all the progress that has been made, many questions remain unanswered. What determines the fate of a star in a binary system? How do the interactions between the components shape the evolution of the system? What role do X-ray binaries play in the broader context of galaxy evolution and cosmic history? These are just a few of the mysteries that continue to drive research in this field. Perhaps the most profound question of all is what X-ray binaries can teach us about the fundamental nature of the universe. These systems are not just astrophysical curiosities. They are windows into the most extreme and enigmatic realms of existence. By studying X-ray binaries, we are not only learning about the cosmos but also pushing the boundaries of human knowledge and understanding. The mysteries surrounding X-ray binaries continue to fuel our fascination, not just because they challenge our understanding of physics, but because they provide a glimpse into phenomena that operate on scales almost impossible to comprehend. These systems exist at the intersection of violent astrophysical processes and the delicate balance of gravitational and electromagnetic forces, offering both chaos and order in equal measure. To unravel their complexities is to journey into the very heart of the universe's most extreme environments. One enduring question involves the role of magnetic fields in shaping the behavior of neutron stars within X-ray binaries. Many neutron stars are observed to have extraordinarily strong magnetic fields, some trillions of times more powerful than the strongest magnets created on Earth. These fields can control the flow of accreted matter, creating hotspots on the star's surface where the infalling material impacts at near-relativistic speeds. These hotspots, in turn, emit X-rays that often pulsate due to the rapid rotation of the neutron star, creating what is known as an X-ray pulsar. The study of these pulsars has revealed a treasure trove of information about neutron star properties, including their magnetic field strength, rotation rates, and even their internal structure. For instance, changes in the timing of X-ray pulses can provide insights into how accretion affects the spin of the neutron star, either speeding it up or slowing it down depending on the direction of angular momentum transfer. Over time, these observations contribute to a deeper understanding of the life cycle of neutron stars and their eventual fates. Black holes in X-ray binaries, on the other hand, present a different set of challenges. Because black holes do not emit light directly, their presence can only be inferred through their gravitational effects on nearby matter. The accretion disk around a black hole can reach incredible temperatures, emitting high-energy X-rays that betray the black hole's location and mass. By studying the motion of material within the disk, astronomers can also estimate the spin rate of the black hole, a key parameter that influences how energy is extracted and radiated from the system. The spin of a black hole is particularly intriguing because it reflects the accumulated history of the system. A rapidly spinning black hole may have gained angular momentum from the accretion of material or the merger with another black hole, while a slower spin may suggest a quieter history. Understanding black hole spin can also shed light on the mechanisms driving relativistic jets, which are thought to be powered, at least in part, by the rotation of the black hole itself. Another area of active research involves the study of intermediate mass black holes, IMBHs, in X-ray binaries. While stellar mass black holes and supermassive black holes are well documented, IMBHs represent a missing link in our understanding of black hole formation and growth. Detecting these elusive objects requires precise measurements of X-ray emission and the dynamics of surrounding material. If confirmed, IMBHs could provide critical insights into how black holes grow from stellar remnants to the behemoths found at the centers of galaxies. The environments surrounding X-ray binaries are also of great interest. These systems are often located in dense stellar regions, such as globular clusters or the cores of galaxies, where interactions with other stars can play a significant role in their evolution. Close encounters with neighboring stars can alter the orbital properties of the binary system, potentially triggering episodes of intense accretion, or even the ejection of one of the components. These interactions add another layer of complexity to the study of X-ray binaries and highlight the importance of considering their broader cosmic context. The high-energy phenomena associated with X-ray binaries also have implications for the interstellar medium, ISM. The intense radiation and particle outflows from these systems can ionize nearby gas, creating bubbles or cavities in the ISM that can be detected through radio or optical observations. These effects contribute to the ongoing cycle of star formation and destruction within galaxies, illustrating the interconnected nature of astrophysical processes on both small and large scales. Despite the wealth of data collected over decades of study, many mysteries persist. For example, the precise mechanisms behind the formation of accretion disks and jets remain a topic of intense debate. How does the material falling toward a compact object transition from a chaotic, turbulent flow to the highly organized structures observed in X-ray binaries? What role do magnetic fields play in channeling and accelerating this material? And how do these processes vary between systems with black hole versus neutron star accretors? Additionally, the evolutionary pathways that lead to the formation of X-ray binaries are not fully understood. While it is clear that massive stars and binary systems can evolve into compact objects through supernova explosions, the details of how these systems survive the explosion and continue to interact remain uncertain. For instance, the loss of mass during a supernova can significantly alter the orbital dynamics of the system, potentially leading to its disruption. Yet many X-ray binaries are observed with tight orbits, suggesting that some mechanism must counteract these disruptive forces. One promising avenue for addressing these questions lies in the study of ultraluminous X-ray sources, ULXs, which are a subset of X-ray binaries with exceptionally high luminosities. While some ULXs are thought to harbor intermediate mass black holes, others appear to involve neutron stars with extraordinarily high accretion rates. These systems push the boundaries of what is thought to be physically possible, challenging existing models of accretion and radiation. By studying ULXs, astronomers hope to uncover new physics that could apply to a broader range of X-ray binaries. Advances in computational modeling have also played a crucial role in advancing our understanding of X-ray binaries. Simulations of accretion flows, disk instabilities, and jet formation have provided valuable insights into the complex interplay of forces that govern these systems. However, these models are only as good as the data used to validate them, underscoring the importance of continued observational efforts. As we look to the future, the prospects for X-ray binary research are brighter than ever. Next-generation observatories, such as the European Space Agency's Athena mission and NASA's proposed Lynx X-ray Observatory, promise to deliver unprecedented sensitivity and resolution, enabling the detection of fainter and more distant X-ray binaries. These instruments will also allow for detailed studies of known systems, uncovering new phenomena and refining existing theories. Moreover, the integration of X-ray binary studies with other areas of astrophysics, such as gravitational wave astronomy and high-energy particle physics, is likely to yield transformative discoveries. By combining data from multiple observatories and across different wavelengths, researchers can build a more complete picture of these enigmatic systems, unlocking their secrets and expanding our understanding of the universe. Ultimately, the study of X-ray binaries is a testament to the power of human curiosity and the drive to explore the unknown. These systems, with their extreme conditions and extraordinary phenomena, challenge us to think beyond the limits of our everyday experience and to confront the fundamental questions of existence. In doing so, they remind us of the vastness of the cosmos and our place within it, a humbling yet inspiring realization that continues to fuel our quest for knowledge. The fascinating interplay of forces within X-ray binaries is not just a testament to their complexity but also a doorway to understanding some of the universe's most extreme conditions. These systems operate in regimes where the laws of physics are pushed to their limits, creating natural laboratories for testing fundamental theories. Every new discovery about X-ray binaries reshapes our understanding of matter, energy, and the cosmos itself. One of the most intriguing aspects of X-ray binaries is the role of relativity in shaping their observed properties. Both general and special relativity come into play when studying these systems. For instance, the intense gravity of a black hole can warp spacetime, creating phenomena such as gravitational redshift, where light emitted near the black hole is stretched to longer wavelengths as it escapes the gravitational pull. Observing this redshift in X-ray binaries allows scientists to measure the strength of the black hole's gravity and gain insights into the nature of spacetime in its vicinity. Neutron stars, with their immense density and strong magnetic fields, are also prime candidates for relativistic effects. One fascinating phenomenon is frame dragging, where the rotation of the neutron star drags the surrounding spacetime along with it. This effect can influence the motion of material in the accretion disk, as well as the paths of emitted X-rays. By studying these relativistic signatures, astronomers can probe the inner workings of neutron stars and test predictions of Einstein's theory of general relativity. Another area of active research involves the interplay between X-ray binaries and gravitational waves. The intense gravitational interactions within these systems can generate ripples in spacetime, especially during events like the merger of two compact objects. While X-ray binaries themselves may not directly produce detectable gravitational waves, they often exist in environments where such events are likely to occur. Observatories like LIGO and Virgo have already detected gravitational waves from merging black holes and neutron stars, and the study of X-ray binaries could provide critical context for interpreting these signals. The high-energy jets observed in some X-ray binaries are another source of fascination. These jets, which can extend for thousands or even millions of kilometers, are thought to be powered by the rotation of the compact object and the accretion disk. Magnetic fields play a crucial role in channeling material into the jets and accelerating it to near-light speeds. Understanding the physics of these jets is not only important for studying X-ray binaries but also for understanding similar phenomena in other astrophysical systems, such as active galactic nuclei and gamma-ray bursts. The variability of X-ray emission in these systems is yet another intriguing feature. Many X-ray binaries exhibit periodic or quasi-periodic oscillations, where the intensity of X-rays fluctuates in a predictable manner. These oscillations are often linked to the dynamics of the accretion disk or the interaction between the disk and the magnetic field of the compact object. By analyzing these patterns, astronomers can infer the properties of the accretion process and gain insights into the physical conditions near the compact object. The discovery of millisecond pulsars, neutron stars with extremely rapid rotation rates, has added another layer of complexity to the study of X-ray binaries. These pulsars are thought to be recycled by accretion from a companion star, which transfers angular momentum to the neutron star and spins it up to incredibly high speeds. Millisecond pulsars emit X-rays as well as radio waves, providing a unique opportunity to study the interaction between accretion and magnetic fields. The study of these objects has also revealed fascinating details about the evolution of binary systems and the end stages of stellar life. One of the most challenging aspects of X-ray binary research is the difficulty of direct observation. These systems are often located in distant regions of the galaxy, and their small size makes them hard to resolve even with powerful telescopes. Instead, astronomers rely on indirect methods, such as analyzing the spectra and variability of emitted X-rays, to infer the properties of these systems. Advances in X-ray astronomy, including the development of more sensitive detectors and higher resolution imaging techniques, have been crucial for overcoming these challenges. Despite these advancements, many questions remain unanswered. For example, the exact mechanism by which accretion disks form and evolve is still not fully understood. While theoretical models provide a framework for understanding disk behavior, the complex interplay of forces within the disk, such as turbulence, magnetic fields, and relativistic effects, makes it difficult to predict their properties with precision. Observational data from X-ray binaries can help refine these models and improve our understanding of disk physics. Another area of uncertainty involves the end stages of X-ray binaries. What happens when the companion star exhausts its fuel and can no longer provide material for accretion? In some cases, the compact object may be left as an isolated black hole or neutron star, while in others, the system may evolve into a different type of binary or even merge into a single object. These evolutionary pathways depend on a variety of factors, including the masses of the components, their separation, and the nature of the surrounding environment. The study of X-ray binaries also has implications for understanding the broader population of compact objects in the universe. By analyzing the distribution and properties of X-ray binaries, astronomers can estimate the number of neutron stars and black holes in our galaxy and gain insights into their formation and evolution. This information is crucial for understanding the life cycles of stars and the role of compact objects in shaping the structure and dynamics of galaxies. One of the most exciting prospects for the future is the potential to study X-ray binaries in other galaxies. While most known systems are located within the Milky Way, advances in observational technology are beginning to reveal X-ray binaries in nearby galaxies, such as the Magellanic Clouds and the Andromeda Galaxy. These extragalactic systems provide a unique opportunity to study X-ray binaries in a variety of environments, offering new perspectives on their formation and behavior. As we continue to explore the mysteries of X-ray binaries, it becomes increasingly clear that these systems are more than just objects of scientific curiosity. They are windows into the fundamental processes that govern the universe. From the extreme conditions near black holes and neutron stars to the intricate dance of matter and energy in accretion disks, X-ray binaries challenge us to push the boundaries of our understanding and to confront some of the deepest questions about the nature of reality. Every new discovery brings us closer to unraveling the secrets of these enigmatic systems, yet each answer also raises new questions, ensuring that the study of X-ray binaries will remain a vibrant and dynamic field of research for years to come. The journey into their mysteries is far from over, and the insights gained from this exploration will undoubtedly continue to illuminate the cosmos in ways we can only begin to imagine. The future of X-ray binary research is poised to be revolutionized by a new generation of telescopes and observatories. These cutting-edge instruments will provide unprecedented insights into the intricate mechanisms driving these systems. Missions like the Athena X-ray Observatory, scheduled for the coming decades, promise to deliver remarkable sensitivity and resolution. With such capabilities, astronomers will be able to detect even the faintest X-ray signals, uncovering hidden systems that were previously undetectable and allowing for more detailed studies of known binaries. One area where Athena and similar observatories will excel is in mapping the structure of accretion disks. By studying how X-rays are emitted and scattered within the disk, researchers can reconstruct its geometry and composition. This is especially important for understanding how material spirals inward toward the compact object and how angular momentum is transferred. Detailed observations of this kind will provide critical tests for theoretical models of accretion, helping to refine our understanding of these dynamic environments. Another key development on the horizon is the use of multi-messenger astronomy to study X-ray binaries. This approach combines observations across different types of signals, such as X-rays, radio waves, and gravitational waves, to create a more complete picture of these systems. For example, the detection of gravitational waves from a neutron star merger within an X-ray binary would provide valuable data about the mass, spin, and orbital dynamics of the system. Such events could also shed light on the conditions required for producing short gamma-ray bursts, which are among the most energetic phenomena in the universe. Radio astronomy will also play a crucial role in advancing our understanding of X-ray binaries. Instruments like the Square Kilometre Array, SKA, will allow for detailed studies of jets and pulsars associated with these systems. Observing the radio emission from jets can reveal how they are launched and how they interact with their surroundings, while high-precision measurements of pulsars can be used to test fundamental physics, such as the equation of state for neutron star matter. In addition to these observational advances, progress in computational astrophysics is enabling more sophisticated simulations of X-ray binaries. By modeling the behavior of matter under extreme conditions, researchers can explore scenarios that are difficult or impossible to observe directly. These simulations are essential for understanding processes like disk instabilities, jet formation, and magnetic field interactions. As computational power continues to grow, the fidelity of these models will improve, allowing for more accurate predictions and deeper insights. The study of X-ray binaries also has implications for broader questions in astrophysics and cosmology. For instance, these systems can serve as standard candles for measuring cosmic distances. By analyzing the properties of X-ray binaries in distant galaxies, astronomers can estimate their distances and use this information to refine measurements of the universe's expansion rate. This, in turn, has implications for understanding dark energy, the mysterious force driving the accelerated expansion of the cosmos. Moreover, X-ray binaries provide a unique perspective on the life cycles of stars and the evolution of galaxies. The presence of these systems in different types of stellar environments, such as star clusters, spiral arms, and galactic halos, can reveal how stars interact with their surroundings and how binary systems evolve over time. By studying the population of X-ray binaries across various galactic environments, researchers can gain insights into the processes that govern star formation, stellar evolution, and the dynamics of galaxies. The interplay between X-ray binaries and their environments is particularly evident in the role they play as sources of feedback. The high-energy radiation and powerful jets produced by these systems can heat surrounding gas, trigger star formation, or suppress it depending on the circumstances. This feedback can influence the evolution of the host galaxy, shaping its structure and regulating its star-forming activity. Understanding these interactions is critical for developing a complete picture of galactic evolution. Despite the incredible progress made in recent years, many mysteries about X-ray binaries remain unresolved. For example, the exact mechanism by which jets are launched and accelerated is still a subject of intense debate. While magnetic fields are thought to play a central role, the details of this process are poorly understood. Similarly, the origin of variability in X-ray emission, especially on very short timescales, remains an open question. These and other challenges ensure that the study of X-ray binaries will continue to be a vibrant and dynamic field of research. As we look to the future, it is clear that the study of X-ray binaries will remain at the forefront of astrophysical research. These systems are not just fascinating in their own right but also serve as key laboratories for exploring fundamental questions about the universe. From testing the limits of relativity to probing the physics of extreme environments, X-ray binaries offer unparalleled opportunities for discovery. Every observation, every simulation, and every theoretical breakthrough brings us one step closer to unlocking their secrets, and in doing so, deepens our understanding of the cosmos. The allure of X-ray binaries lies not only in their scientific significance but also in their ability to inspire wonder and curiosity. They remind us of the extraordinary complexity and beauty of the universe, and of the limitless possibilities for exploration and discovery that lie ahead. As we continue to unravel their mysteries, we are not just advancing our knowledge of the cosmos, we are also expanding the horizons of human imagination and redefining our place in the grand tapestry of existence. The next frontier in the study of X-ray binaries may also involve the search for unique and rare systems that challenge existing paradigms. Among the most fascinating possibilities are systems with exotic compact objects, such as quark stars or even hypothetical entities like gravastars. Quark stars, if they exist, represent an even denser state of matter than neutron stars, composed almost entirely of free quarks. Detecting such systems within X-ray binaries would revolutionize our understanding of matter under extreme conditions and open new avenues for exploring the physics of the strong nuclear force. Additionally, astronomers are keenly interested in identifying binaries with very low-mass black holes. The smallest black holes discovered so far hover around the lower mass limit predicted by stellar evolution models, roughly 3 to 5 solar masses. However, if even smaller black holes exist, they would challenge these models and force a re-evaluation of our understanding of how massive stars collapse. Finding such systems in X-ray binaries could provide direct evidence for these elusive objects. The discovery of unusual accretion behaviors in X-ray binaries also continues to surprise researchers. For example, some binaries exhibit super-Eddington accretion, where the inflow of matter onto the compact object exceeds the theoretical limit for stable accretion. How such systems maintain stability and avoid blowing away the excess material remains a topic of intense investigation. These extreme accretion rates are often accompanied by extraordinarily luminous X-ray emissions, leading to the classification of these systems as ultraluminous X-ray sources, ULXs. While many ULXs are thought to host black holes, some may contain neutron stars capable of generating such intense emissions due to their powerful magnetic fields. Another puzzling phenomenon observed in some X-ray binaries is the periodic switching between different accretion states. These state changes are often accompanied by dramatic shifts in X-ray spectra and luminosity, as well as the appearance or disappearance of radio jets. The underlying mechanisms driving these transitions are not fully understood, but they are believed to involve complex interactions between the accretion disk, the magnetic field, and the compact object. Investigating these phenomena further will shed light on the dynamic processes governing accretion and jet formation. The potential for discovering new types of compact objects within X-ray binaries is not limited to black holes and neutron stars. There is growing interest in exploring the possibility of primordial black holes as components of these systems. Primordial black holes are hypothetical remnants of the early universe, formed shortly after the Big Bang through density fluctuations. If they exist, they could be detectable in binary systems, where they would behave similarly to stellar mass black holes but with distinct mass distributions and formation histories. Detecting such objects in X-ray binaries would provide a unique window into the conditions of the early universe. Meanwhile, studies of X-ray binaries continue to intersect with broader questions about the evolution of binary star systems. For instance, the processes that lead to the formation of a compact object in a binary system often involve episodes of mass transfer and common envelope evolution. These stages are not only critical for the formation of X-ray binaries but also play a role in the creation of other exotic systems, such as double neutron stars and gravitational wave sources. Understanding these processes requires detailed modeling and observations of both pre- and post-supernova binaries. The role of magnetic fields in X-ray binaries is another area ripe for exploration. Many neutron stars in these systems possess incredibly strong magnetic fields, which can influence the behavior of accreting matter in profound ways. For instance, the magnetic field can channel the accretion flow onto the magnetic poles of the neutron star, creating hotspots that emit pulsating X-rays. These X-ray pulsars provide valuable information about the magnetic field strength, rotation rate, and surface conditions of the neutron star. Moreover, understanding the evolution of magnetic fields in these systems is key to unraveling the life cycles of neutron stars. Beyond the physics of individual systems, the demographics of X-ray binaries across different stellar populations provide valuable clues about their origins and evolution. For example, the abundance and properties of X-ray binaries in globular clusters differ significantly from those in the field. This difference is attributed to the high stellar densities in globular clusters, which facilitate interactions between stars and binaries, leading to the formation of compact binaries through processes like tidal capture and exchange interactions. Studying these systems in diverse environments helps astronomers piece together the complex puzzle of binary evolution. The implications of X-ray binary research extend even further, intersecting with cosmology, high-energy astrophysics, and the study of fundamental forces. For instance, X-ray binaries can serve as natural laboratories for testing general relativity in strong gravitational fields. Observations of the orbital motion of companion stars around black holes provide some of the most precise tests of relativistic effects, such as frame dragging and gravitational redshift. These measurements help refine our understanding of gravity and test the predictions of Einstein's theory in regimes where it has yet to be fully validated. In addition to testing relativity, X-ray binaries contribute to our understanding of the life cycles of galaxies. The energy released by these systems, especially in the form of jets and high-energy radiation, can influence the interstellar medium and regulate star formation. This feedback process is particularly evident in starburst galaxies, where the combined output of many X-ray binaries and other high-energy sources can shape the galaxy's evolution. By studying the collective impact of X-ray binaries in different galactic environments, researchers can gain insights into the interplay between stars, compact objects, and the larger structures they inhabit. As technology advances and new observatories come online, the pace of discovery in the field of X-ray binaries is set to accelerate. From uncovering new classes of objects to probing the physics of extreme environments, the study of these systems continues to push the boundaries of our understanding. At the same time, the mysteries that remain unsolved ensure that X-ray binaries will remain a focal point for astronomical research for decades to come. These systems not only illuminate the universe with their extraordinary X-ray emissions but also illuminate the human spirit's relentless pursuit of knowledge. In their enigmatic behavior, they challenge us to look deeper, think harder, and dream bigger. They remind us that even in the vastness of the cosmos, every small piece of the puzzle holds profound significance, and every discovery brings us closer to understanding the grand design of existence. The deeper we dive into the mysteries of X-ray binaries, the more interconnected they seem with broader cosmic phenomena. For instance, the study of these systems has shed light on the processes responsible for producing heavy elements in the universe. Supernova explosions and neutron star mergers, both closely tied to the life cycles of X-ray binaries, are the primary sites for synthesizing elements heavier than iron, such as gold, platinum, and uranium. By understanding the conditions under which X-ray binaries form and evolve, astronomers can trace the cosmic origins of these elements and their distribution across galaxies. Moreover, the high-energy jets produced by some X-ray binaries are of particular interest for their potential role in shaping the intergalactic medium. These jets, often moving at relativistic speeds, can inject vast amounts of energy and material into their surroundings. In doing so, they may influence the temperature, density, and chemical composition of interstellar and intergalactic gas, creating a feedback loop that regulates star formation and galaxy evolution. This phenomenon, sometimes referred to as X-ray binary feedback, is thought to be especially significant in young, star-forming galaxies. Interestingly, X-ray binaries also provide critical insights into the mysterious nature of dark matter. While they are not direct sources of evidence for dark matter, the distribution and behavior of X-ray binaries in galaxies can indirectly reveal clues about the gravitational effects of this elusive substance. For example, The spatial arrangement of X-ray binaries in a galaxy's halo may reflect the underlying distribution of dark matter, offering a unique perspective on its influence. Another intriguing avenue of research involves the potential connections between X-ray binaries and gamma-ray bursts, GRBs. GRBs are some of the most energetic events in the universe, thought to originate from the collapse of massive stars or the merger of compact objects like neutron stars. Some models suggest that certain types of X-ray binaries could be progenitors of these bursts. By studying X-ray binaries in detail, scientists hope to better understand the conditions that lead to GRBs and their subsequent impact on the cosmos. The field of X-ray binary research is also being revolutionized by advancements in multi-messenger astronomy. This approach combines data from different types of signals, such as electromagnetic waves, gravitational waves, and neutrinos, to provide a more comprehensive picture of astrophysical phenomena. For example, the detection of gravitational waves from neutron star mergers has opened new doors for studying the life cycles of compact binary systems. These mergers are not only spectacular events in their own right but also the endpoints of certain X-ray binary evolution paths. By combining X-ray observations with gravitational wave data, researchers can piece together the full story of how these systems form, evolve, and ultimately merge. The future of X-ray binary studies also lies in exploring systems beyond our galaxy. While most known X-ray binaries are located in the Milky Way or nearby galaxies like the Magellanic Clouds, technological advancements are enabling the detection of these systems at much greater distances. Observing X-ray binaries in distant galaxies provides a unique opportunity to study their properties across a wide range of environments, from low metallicity star-forming regions to dense, ancient stellar populations. These observations can reveal how the characteristics of X-ray binaries vary with cosmic time and environment, offering valuable insights into the universality of their underlying physics. At the same time, the detailed study of individual X-ray binaries within our own galaxy remains a cornerstone of the field. Each system is a unique laboratory for exploring extreme physics, from the behavior of matter under intense gravitational and magnetic fields to the processes governing accretion and jet formation. High-resolution observations, particularly with instruments like the Chandra X-ray Observatory and XMM Newton, continue to uncover new details about these fascinating systems, from the structure of their accretion disks to the properties of their compact objects. The quest to understand X-ray binaries also intersects with the search for extraterrestrial life. While this connection may not be immediately obvious, the high-energy radiation emitted by these systems can influence the habitability of planets in their vicinity. For example, intense X-ray and gamma-ray emissions from a nearby binary could strip away the atmospheres of planets, making them inhospitable for life as we know it. Conversely, the study of X-ray binaries can help identify regions of space where such high-energy environments are absent, potentially guiding the search for life-friendly star systems. As we continue to unravel the mysteries of X-ray binaries, it becomes increasingly clear that these systems are not just isolated phenomena but integral components of the cosmic tapestry. They connect to a wide range of astrophysical processes, from the formation of elements to the evolution of galaxies and the dynamics of the universe itself. Each discovery adds a new thread to this intricate web, revealing a universe that is as interconnected as it is vast. The pursuit of knowledge about X-ray binaries is a testament to humanity's insatiable curiosity and our ability to probe the cosmos in ever more sophisticated ways. With each new observation, we inch closer to answering some of the most profound questions about our universe. How do stars live and die? What happens to matter under the most extreme conditions? And how do these processes shape the cosmos as a whole? While much has been learned about X-ray binaries, many mysteries remain. For instance, the precise mechanisms driving certain types of variability in these systems are still not fully understood. Why do some systems exhibit quasi-periodic oscillations, while others remain steady for long periods? What causes sudden, dramatic changes in brightness in some X-ray binaries? These questions are at the forefront of current research, promising new insights and surprises in the years to come. Ultimately, the study of X-ray binaries exemplifies the power of scientific inquiry to illuminate the unknown. These enigmatic systems challenge our understanding, push the boundaries of technology, and inspire us to look beyond the familiar. They remind us that even in the darkest corners of space, there is light, both literal and metaphorical, waiting to be discovered. The fascinating world of X-ray binaries holds even more untold stories as we venture deeper into the mysteries of these cosmic systems. Beyond their intrinsic beauty and complexity, X-ray binaries serve as a window into the most extreme environments imaginable, allowing scientists to probe phenomena that push the boundaries of physics. One of the most profound aspects of studying X-ray binaries lies in the way they challenge our understanding of general relativity and quantum mechanics. The behavior of matter in these systems, particularly the way it interacts with the powerful gravitational and magnetic fields near black holes and neutron stars, can test the limits of current theories. Take, for example, the behavior of matter in the accretion disks around these compact objects. These disks, often made up of hot gas and dust spiraling toward the black hole or neutron star, exhibit fascinating phenomena that can help us understand how matter behaves in the face of incredibly strong forces. In particular, the so-called no-hair theorem of black holes is being tested in the context of X-ray binaries. This theorem suggests that black holes can be completely characterized by just three properties: their mass, spin, and electric charge. However, the discovery of complex X-ray spectra coming from the inner regions of the accretion disks, where relativistic effects are most pronounced, suggests that these regions may be more complex than previously thought. Some researchers believe that understanding the behavior of X-ray emission from these areas could help reveal whether black holes really do conform to the no-hair theorem, or if there are other factors at play that we haven't yet considered. In addition to testing fundamental theories of physics, X-ray binaries are also helping scientists probe the enigmatic behavior of matter under extreme conditions. For instance, in some cases, matter in these systems can be compressed to densities approaching that of an atomic nucleus. These ultra-dense environments provide a unique laboratory for studying nuclear physics in ways that cannot be replicated on Earth. This is especially true in the case of neutron stars, where the matter inside is thought to exist in an exotic state known as neutronium. The equation of state for neutron star matter remains one of the biggest unsolved problems in physics, and studying X-ray binaries could provide crucial data to constrain the properties of this mysterious substance. The magnetic fields associated with X-ray binaries also offer a wealth of insight into the behavior of matter in the presence of extreme magnetic forces. In many of these systems, particularly those containing neutron stars, the magnetic fields are so strong that they can affect the accretion flow and alter the emission of X-rays in ways that are still not fully understood. The complex interplay between the magnetic field, the accretion disk, and the companion star creates a dynamic environment that could shed light on the nature of magnetars, neutron stars with extremely powerful magnetic fields, and other highly magnetic astronomical objects. X-ray binaries also play a key role in our understanding of stellar evolution. The fate of a star depends heavily on its mass, and understanding how massive stars interact with companion objects in a binary system is crucial for mapping out the evolution of these stars. In particular, when a massive star becomes a supernova and leaves behind a compact object like a black hole or neutron star, it can lead to the formation of an X-ray binary. The way these systems evolve, whether they undergo dramatic outbursts or remain relatively stable, can provide clues about the nature of stellar death and the birth of compact objects. This process is integral to understanding how stellar populations evolve across galaxies and how the most extreme objects in the universe come into being. As we continue to explore the realm of X-ray binaries, the question of their potential to host extraterrestrial life arises. While X-ray binaries themselves are highly hostile environments due to the intense radiation they emit, the study of these systems may help refine our understanding of the conditions required for life elsewhere in the universe. The extreme environments of X-ray binaries could provide a unique perspective on what makes a planet or moon habitable. Understanding the radiation environments of exoplanets in distant star systems, for example, might help scientists identify the types of stars and planetary systems that are most likely to support life. In a way, studying these extreme binary systems is akin to studying the outer limits of life in the universe. Despite the complexity and harsh conditions surrounding X-ray binaries, These systems are also intriguing for the broader story they tell about the nature of the universe. They serve as a reminder that the cosmos is far from a static, peaceful place. Instead, it is a dynamic, ever-evolving system of forces and phenomena that are constantly interacting with one another. From the formation of black holes and neutron stars to the violent bursts of X-ray radiation that characterize these systems, X-ray binaries paint a picture of a universe in motion. The next frontier in X-ray binary research lies in the development of next-generation telescopes and observatories, both on the ground and in space. Instruments like the James Webb Space Telescope, JWST, the Advanced LIGO detectors for gravitational waves, and the upcoming Athena X-ray Observatory will all play key roles in advancing our understanding of these cosmic systems. With their enhanced sensitivity and resolution, these instruments will be able to detect more distant and fainter X-ray binaries, opening up new possibilities for discovery. The potential for breakthroughs in this field is immense, and we are likely to see many exciting revelations in the coming decades. It's important to recognize the role that these systems play in shaping our understanding of the universe. They are far more than just distant objects emitting high-energy radiation. They are the cosmic laboratories where the most extreme conditions in nature unfold. They challenge our understanding of physics, inspire new technologies, and offer a glimpse into the ultimate fate of stars and matter. In many ways, they represent the frontier of human knowledge, pushing the boundaries of what we know about the cosmos and ourselves. The mysteries surrounding X-ray binaries are far from solved, and with each new discovery, we unlock more pieces of the puzzle. As our tools and techniques become ever more sophisticated, we are likely to uncover new layers of understanding about these systems, shedding light on the fundamental processes that govern the universe. The story of X-ray binaries is a testament to the relentless pursuit of knowledge and the power of scientific inquiry to reveal the most profound mysteries of the cosmos. X-ray binaries, as we have seen, are not just fascinating for their inherent extremes but also because they offer a laboratory for testing our understanding of the universe in ways few other phenomena can. As we look forward to the next stage of X-ray binary research, there are several aspects that will drive scientific progress, each offering new insights into both the known and unknown realms of astrophysics. One of the most intriguing questions remaining is how X-ray binaries can inform us about the formation and evolution of black holes. While much has been learned, we are still working to fully understand how these enigmatic objects evolve over time, particularly in binary systems. Are all black holes born from the collapse of massive stars, or can they form in other ways? How do they grow and interact with their surroundings as they accumulate mass from a companion star? Observing these processes in action, particularly in systems where a neutron star or black hole pulls material from a nearby companion, can offer insights into the growth mechanisms of these objects. Understanding the precise details of this process is essential for making progress in our broader understanding of black holes, their spin, and their role in galaxy formation. Moreover, the question of how a black hole's mass affects its interaction with the surrounding accretion disk remains an open one. The growing body of data obtained from studying X-ray binaries offers a unique opportunity to explore this. As material from the companion star spirals toward the black hole, it heats up and emits X-rays due to the extreme gravitational forces. However, the precise way in which the black hole's mass and spin affect this radiation is still not completely understood. Some scientists believe that the amount of material accumulating on a black hole's surface may influence the formation of jets, or even the pattern of the X-ray emissions themselves. These insights could lead to breakthroughs in how we perceive the dynamics of matter in extremely strong gravitational fields. Another exciting frontier lies in the study of the relativistic jets that often accompany X-ray binaries. These jets are emitted along the rotational axis of the black hole or neutron star and can stretch across vast regions of space. Although they have been observed for decades, the mechanisms that drive them are still not entirely clear. One theory posits that the magnetic fields around the compact object play a significant role in shaping these jets. As material in the accretion disk moves toward the black hole or neutron star, it is often channeled by the powerful magnetic fields into narrow beams of relativistic particles that travel at speeds close to the speed of light. Studying these jets in detail could reveal much about the structure and behavior of black holes, as well as offer a glimpse into how they interact with the interstellar medium. Relativistic jets are often observed in systems where the compact object is actively accreting material, but these jets aren't exclusive to X-ray binaries. In fact, similar jets have been detected in active galactic nuclei AGN, where supermassive black holes play a role in powering the jets. The commonalities between X-ray binaries and AGN suggest that studying one could help to unlock the mysteries of the other. It's possible that the mechanisms that drive jet formation in X-ray binaries might be similar to those in the cores of galaxies, offering a unique opportunity to understand how different types of black holes interact with their environments across different scales. The discovery of intermediate mass black holes in some X-ray binary systems could also significantly alter our understanding of black hole formation. While supermassive black holes in the centers of galaxies and stellar mass black holes formed from collapsing stars are well known, intermediate mass black holes are more elusive. These black holes, with masses between a few hundred and several thousand times that of the Sun, could bridge the gap between the two types of black holes, helping us understand the full range of black hole masses. As researchers continue to observe X-ray binaries, they may find evidence that could confirm the existence of these elusive objects, providing insight into their formation processes and their role in the broader context of astrophysical evolution. As the field of X-ray binary research continues to advance, so too does the technology that allows us to observe these distant, powerful objects. Ground-based observatories, like the upcoming Extremely Large Telescope, ELT, promise to help us study these systems with unprecedented detail. However, it's the space-based observatories that will play the most critical role in observing X-ray binaries. The Chandra X-ray Observatory, launched in 1999, and the upcoming Athena mission, set to launch in the early 2030s, will offer critical insights into the high-energy environments surrounding compact objects. Athena, in particular, promises to be a game-changer, with a significantly larger mirror area and more advanced instruments capable of detecting X-rays with unprecedented precision. These missions will enable us to probe the very heart of X-ray binaries, shedding light on the processes taking place within these extreme systems. Gravitational wave astronomy also has the potential to open up an entirely new dimension of discovery in X-ray binary systems. While gravitational waves are most commonly associated with black hole mergers, they can also be produced by the interactions in X-ray binary systems, especially when a neutron star is involved. The LIGO and Virgo collaborations have already detected gravitational waves from black hole mergers, and the detection of similar waves from X-ray binary systems could provide an entirely new way of studying these systems. Gravitational wave signals could offer key insights into the masses, spins, and orbital parameters of the compact objects in these systems, further expanding our understanding of their behavior. As we continue to study X-ray binaries, the possibility of new, unforeseen discoveries looms large. One potential breakthrough is the detection of fast radio bursts, FRBs, in X-ray binaries. These mysterious bursts of radio emission, which have been detected in recent years, could have an even closer connection to X-ray binaries than previously realized. While the exact cause of FRBs remains a topic of debate, some researchers suspect that they may be linked to the extreme conditions in systems containing neutron stars, potentially interacting with the X-ray emissions in ways we are just beginning to understand. X-ray binaries are more than just sources of high-energy radiation. They are laboratories for testing the most fundamental principles of physics. By studying these systems, we are not only learning about the evolution of stars and the formation of compact objects, but also uncovering the deepest mysteries of the universe. As we continue to explore these systems, we can expect new technologies, new discoveries, and above all, new questions that will continue to drive the quest for knowledge. The more we uncover about X-ray binaries, the more we realize that the universe is not just a vast expanse of empty space but a complex and dynamic environment in which matter, energy, and forces interact in extraordinary ways. From the birth and death of stars to the formation of black holes and neutron stars, X-ray binaries give us a glimpse into the life cycles of the most extreme objects in the universe. In doing so, they inspire awe, wonder, and the insatiable desire to understand the cosmos in all its complexity. As we delve further into the mysteries of X-ray binaries, it becomes clear that the interactions between compact objects and their companion stars are not merely processes of accretion, but rich environments that provide a detailed picture of extreme physics in action. The energy radiated from these systems provides critical data that can enhance our understanding of fundamental processes, such as the behavior of matter under intense gravitational and magnetic forces. One of the most remarkable aspects of X-ray binaries is their ability to test Einstein's theory of general relativity in extreme conditions. In a typical binary system, the companion star's gravity causes its orbit to change over time, but in the case of X-ray binaries, these objects are subject to such intense forces that the effects of relativity become pronounced. When material from the companion star is pulled towards the black hole or neutron star, it is accelerated to speeds approaching the speed of light. As a result, the space around the compact object becomes warped, and time itself begins to stretch. Observations of this warping, particularly in the form of the X-ray radiation emitted from the system, allow scientists to test the predictions of general relativity in ways that cannot be done on Earth. In addition to testing general relativity, X-ray binaries also provide valuable insights into quantum mechanics, particularly the behavior of matter in the extreme environments near black holes and neutron stars. The intense gravitational fields present in these systems push the boundaries of our understanding of quantum gravity, a field that seeks to reconcile the laws of quantum mechanics with those of general relativity. By studying X-ray binaries, we can gain a better understanding of how the two interact, potentially unlocking new insights into the very fabric of spacetime itself. Moreover, X-ray binaries are not just fascinating because of the gravitational forces at play. They also reveal a great deal about the material composition of the systems involved. The companion star, often a massive, luminous object, is an essential component of the system, and its material is funneled into the accretion disk of the compact object. The study of these disks, which are made of hot, ionized gas, provides a window into the nature of the material at the most extreme temperatures and densities known in the universe. By analyzing the X-ray spectra emitted by the system, scientists can determine the chemical composition of the accretion disk and learn about the processes that govern the formation and destruction of elements in such extreme environments. The interplay between the companion star and the compact object is also a subject of intense study. While it's well known that the compact object accretes matter from its companion star, the exact mechanism through which this transfer of material occurs remains an open question. In many X-ray binaries, the companion star loses mass via a process called Roche-Lobe overflow, in which material from the star is pulled toward the compact object by the intense gravitational pull. This material forms an accretion disk around the black hole or neutron star, but the details of how the material is channeled into the disk, and how it interacts with the magnetic fields of the compact object, remain an area of active research. One of the most puzzling phenomena in X-ray binary systems is the existence of type I X-ray bursts, which are sudden and intense bursts of X-rays that occur on the surface of neutron stars. These bursts are thought to be caused by the rapid fusion of accumulated hydrogen or helium in a process known as thermonuclear runaway. The study of these bursts provides valuable information about the internal structure of neutron stars, including the properties of the material that makes up their dense cores. These bursts are so powerful that they can temporarily outshine the entire binary system, making them an important tool for understanding the extreme conditions at the surface of neutron stars. In addition to type I X-ray bursts, there are also more mysterious and enigmatic events that occur in X-ray binaries. For instance, some systems exhibit quasi-periodic oscillations (QPOs) in their X-ray emission. These oscillations, which occur at specific frequencies, are thought to be related to the dynamics of the accretion disk and the magnetic fields around the compact object. The cause of these oscillations is still not fully understood, but their study could provide valuable insights into the physical processes that govern the behavior of matter in such extreme environments. Another interesting aspect of X-ray binaries is the way in which they contribute to our understanding of stellar evolution. The companion stars in these systems provide valuable information about the life cycle of stars, especially in terms of how they evolve under the influence of their massive companion. For instance, the transfer of material from the companion star can accelerate the evolution of the star itself, possibly altering its structure and composition in ways that would not occur in a single star system. By studying these interactions, astronomers can gain a deeper understanding of how stars evolve in the presence of a massive companion, providing a unique perspective on stellar life cycles. The study of X-ray binaries also holds promise for understanding the processes that govern the formation of supernovae and gamma-ray bursts, which are among the most energetic events in the universe. Many of these events are thought to be triggered by the collapse of massive stars, often in binary systems, and understanding the behavior of X-ray binaries may help to shed light on the complex dynamics that lead to these explosive phenomena. In particular, the study of the accretion process in X-ray binaries could reveal more about the conditions that precede the violent deaths of stars, offering new clues about the formation of these powerful cosmic events. One of the most exciting developments in recent years has been the detection of gravitational waves, ripples in space-time caused by the acceleration of massive objects. While gravitational waves have mostly been associated with the collision of black holes or neutron stars, it's also possible for X-ray binaries to produce these waves, albeit at a lower amplitude. The detection of gravitational waves from X-ray binaries could provide a new avenue for studying these systems, offering insights into their mass, spin, and orbital parameters. Furthermore, gravitational waves could reveal information about the behavior of matter in the extreme environments near black holes and neutron stars, offering a completely new way of observing these distant systems. As our technology advances, the tools available for observing X-ray binaries continue to improve. The upcoming James Webb Space Telescope, with its ability to observe infrared and X-ray wavelengths, will be a crucial tool for exploring these systems in greater detail. Additionally, the planned LISA, Laser Interferometer Space Antenna, mission, which aims to detect gravitational waves in space, could open up entirely new possibilities for studying X-ray binaries and the extreme phenomena they exhibit. These upcoming missions hold the potential to revolutionize our understanding of X-ray binaries and compact objects, providing the opportunity to explore new regions of space and time with unprecedented sensitivity. As we look to the future, there's no telling what new mysteries will be uncovered in the study of X-ray binaries. What is certain is that these systems will continue to challenge our understanding of the universe, offering new insights into the nature of black holes, neutron stars, and the fundamental forces that govern the cosmos. The more we learn about X-ray binaries, the more we realize how much we still have to discover about these enigmatic systems. In the years to come, these discoveries will undoubtedly continue to reshape our understanding of the universe and our place within it. X-ray binaries are far more than just fascinating cosmic objects. They are key to unlocking some of the most profound mysteries of the universe. Through their study, we are not just learning about black holes and neutron stars. We are exploring the very nature of space, time, and matter itself. As we continue to push the boundaries of our knowledge, we can expect that the secrets of X-ray binaries will continue to captivate and inspire generations of scientists, astronomers, and curious minds around the world. The universe is full of mysteries, but with X-ray binaries, we are beginning to peel back the veil of the unknown, revealing the deepest secrets of the cosmos. As the study of X-ray binaries continues to evolve, one of the most significant avenues of research lies in the nature of their compact objects, black holes and neutron stars. These enigmatic objects, despite their extreme conditions, hold crucial clues to understanding the most fundamental forces of nature. The unique characteristics of black holes and neutron stars, when observed in the context of X-ray binaries, allow scientists to probe the behavior of matter under some of the most extreme conditions in the universe. Let's begin with black holes. These objects, with gravitational pulls so strong that not even light can escape, are often the centerpiece of X-ray binaries. When a star companion is in close enough proximity, its matter is drawn towards the black hole, forming an accretion disk around the event horizon. As the gas spirals in, it heats up to millions of degrees, emitting vast amounts of energy in the form of X-rays. The exact nature of this process is still a subject of active research, but one thing is clear: black holes and X-ray binaries provide a natural laboratory for testing our understanding of general relativity. Through the observation of the X-ray emissions and the way in which they change over time, astronomers can infer the size, mass, and spin of the black hole. These measurements are key in understanding the physics of black holes and, in turn, shedding light on the fundamental nature of space and time. Recent advancements in gravitational wave astronomy, particularly the detection of merging black holes, have opened new possibilities for studying black holes in X-ray binaries. When two black holes in a binary system merge, they release a tremendous amount of energy, rippling through space-time and producing gravitational waves that can be detected by observatories like LIGO and Virgo. These events, known as binary black hole mergers, offer the potential for new insights into the properties of black holes that were previously inaccessible. By analyzing the gravitational wave signals produced during a merger, scientists can learn about the masses, spins, and orbital dynamics of the black holes involved. This information can then be compared with the data obtained from X-ray binary systems, providing a more comprehensive understanding of how black holes behave in different environments. The study of neutron stars in X-ray binaries is similarly crucial for understanding the behavior of matter under extreme conditions. Neutron stars, the remnants of massive stars that have undergone supernova explosions, are incredibly dense objects. A typical neutron star has a mass about 1.4 times that of the Sun, but it is compressed into a sphere just 10 to 20 kilometers in radius. The density inside a neutron star is so high that a single cubic centimeter of neutron star material would weigh about 400 million tons on Earth. When a neutron star is part of an X-ray binary system, the intense gravitational field of the star can strip material from the companion star and funnel it into an accretion disk. As the matter falls toward the neutron star, it heats up to extreme temperatures, emitting X-rays that can be detected by telescopes. The study of these X-ray emissions offers valuable insights into the internal structure of neutron stars, including their magnetic fields, rotation rates, and the state of matter inside the star. One of the most fascinating aspects of neutron stars in X-ray binaries is their ability to exhibit a variety of different behaviors, depending on the rate at which they accrete material. Some neutron stars are classified as bursting sources, as they occasionally emit intense bursts of X-rays, known as Type 1 X-ray bursts. These bursts are thought to be caused by thermonuclear explosions on the surface of the neutron star, as accumulated material undergoes rapid fusion. The study of these bursts can provide valuable information about the composition and structure of neutron stars, as well as the physical processes that occur under such extreme conditions. Another intriguing feature of neutron stars in X-ray binaries is the phenomenon of millisecond X-ray pulsars. These objects are rotating neutron stars that emit regular pulses of X-rays as their magnetic fields sweep through space. The frequency of these pulses is incredibly high, with some millisecond pulsars spinning hundreds of times per second. The study of these pulsars can reveal important information about the interior structure of neutron stars, as well as the mechanisms that govern their rotation and magnetic fields. The interaction between the compact object and its companion star in an X-ray binary also has profound implications for the evolution of both stars. As material is siphoned off the companion star and accreted by the compact object, the companion star experiences significant changes in its structure and behavior. Over time, the loss of mass from the companion star can alter its size, luminosity, and even its eventual fate. In some cases, the companion star may eventually be completely consumed by the compact object, resulting in the formation of a binary system in which the compact object is the sole remaining member. The fate of the companion star in an X-ray binary is largely determined by its mass and the rate at which it loses material to the compact object. For instance, in a low-mass X-ray binary system, the companion star may survive for a much longer period, with material gradually being siphoned off over time. In contrast, in a high-mass X-ray binary system, the companion star may quickly lose its mass, eventually evolving into a supernova and possibly triggering the formation of a new compact object, such as a neutron star or black hole. The interaction between the compact object and the companion star can also lead to the formation of strong magnetic fields and intense radiation, which can have profound effects on the surrounding environment. In some cases, the accretion disk surrounding the compact object can become so hot and energetic that it emits jets of relativistic particles, which can extend for vast distances into space. These jets, known as relativistic jets, are thought to be powered by the rotation of the compact object and the intense magnetic fields that surround it. The study of these jets is another fascinating aspect of X-ray binaries. By analyzing the X-ray and radio emissions from these systems, astronomers can learn about the composition, structure, and behavior of relativistic jets. These jets are believed to play a key role in the evolution of galaxies, as they can transport energy and matter over vast distances, potentially influencing the growth and dynamics of supermassive black holes at the centers of galaxies. In recent years, the detection of gravitational waves has opened up new possibilities for studying X-ray binaries. Gravitational waves, which are ripples in spacetime caused by the acceleration of massive objects, can be produced by the merger of compact objects, such as black holes and neutron stars. By detecting these waves, scientists can learn about the properties of the objects involved in the merger, as well as the dynamics of the binary system leading up to the collision. One of the most exciting aspects of gravitational wave astronomy is the potential to study the extreme environments around black holes and neutron stars in ways that are not possible with traditional electromagnetic observations. Gravitational waves offer a unique window into the universe, allowing scientists to observe phenomena that are otherwise hidden behind the event horizons of black holes or the dense cores of neutron stars. By combining gravitational wave data with X-ray observations, astronomers can gain a more complete picture of the behavior of compact objects in X-ray binary systems. As we continue to improve our observational capabilities, the study of X-ray binaries will undoubtedly yield more insights into the nature of the universe. The combination of X-ray, gravitational wave, and radio observations, along with advances in theoretical modeling, will allow scientists to probe the most extreme conditions known in the cosmos. From testing the limits of general relativity to studying the behavior of matter under extreme conditions, X-ray binaries remain one of the most exciting and valuable areas of research in modern astrophysics. Through the study of these remarkable systems, we are not only learning about the fundamental physics of black holes and neutron stars, but we are also gaining a deeper understanding of the universe itself. X-ray binaries challenge our understanding of space, time, and matter, and as we continue to explore these systems, we will undoubtedly uncover more mysteries that will push the boundaries of human knowledge. As we continue to uncover the mysteries of X-ray binaries, we begin to realize just how complex and enigmatic these systems truly are. The sheer diversity of behaviors exhibited by these systems, ranging from intense bursts of energy to steady, continuous radiation, is a testament to the variety of interactions that can take place between compact objects and their companion stars. This diversity offers us a unique opportunity to study astrophysical processes in real time, observing how matter behaves under extreme conditions and how it can give rise to powerful phenomena like X-ray emissions, jets, and even gravitational waves. One of the key factors that influences the behavior of X-ray binaries is the rate at which material is accreted by the compact object. This rate can vary greatly depending on the mass and composition of the companion star, as well as the orbital characteristics of the system. In some systems, the material is accreted at a relatively slow rate, leading to steady X-ray emissions that can be observed over long periods of time. In other systems, however, the accretion rate can spike dramatically, leading to outbursts of X-rays that can be seen as sudden increases in brightness. These outbursts are often the result of the material in the accretion disk reaching critical conditions, where the buildup of matter triggers a release of energy. This release can take the form of an X-ray flare or a more violent explosion, known as an X-ray nova. X-ray novae are short-lived events that can last from a few days to a few weeks, during which the system experiences a dramatic increase in brightness. The cause of these outbursts is still not fully understood, but it is thought to be related to changes in the structure of the accretion disk, which can become unstable under certain conditions. One of the most fascinating aspects of X-ray binaries is the ability of these systems to emit X-rays across a wide range of energies. The X-ray spectrum of a binary system can reveal crucial information about the physical conditions in the accretion disk and the surrounding environment. For example, high-energy X-rays can be produced by the intense gravitational forces near the compact object, while lower-energy X-rays may be emitted by the gas in the outer regions of the accretion disk. By studying the detailed shape of the X-ray spectrum, astronomers can gain insights into the temperature, density, and composition of the material surrounding the compact object. In addition to their X-ray emissions, many X-ray binaries also exhibit radio emissions. These radio waves are often associated with the relativistic jets that are produced by the compact object. As the accretion disk funnels material toward the compact object, powerful magnetic fields can accelerate particles to nearly the speed of light, creating jets of high-energy particles that emit radiation across the electromagnetic spectrum. The study of these jets provides valuable information about the physics of accretion and the mechanisms that govern the behavior of matter in these extreme environments. One of the most intriguing aspects of X-ray binaries is the role they play in the evolution of their host galaxies. As compact objects accrete matter from their companion stars, they release vast amounts of energy, which can have a significant impact on the surrounding gas and dust. This energy can drive powerful winds and outflows, which can heat and ionize the gas, preventing it from collapsing to form new stars. In this way, X-ray binaries can play a role in regulating star formation within their host galaxies, acting as feedback mechanisms that influence the evolution of the galactic ecosystem. Furthermore, the energy released by X-ray binaries can also contribute to the growth of supermassive black holes at the centers of galaxies. In some cases, the accretion of matter onto a black hole can produce powerful outflows and jets that carry energy and matter away from the central region of the galaxy. These outflows can influence the surrounding gas and dust, regulating the formation of new stars and potentially preventing the black hole from growing too quickly. This feedback loop between compact objects, their companion stars, and the broader galactic environment is an area of active research, as scientists strive to understand the complex relationships between these different components of the galaxy. The study of X-ray binaries also has profound implications for our understanding of the fundamental physics of compact objects. These systems allow scientists to test theories of gravity, matter, and energy in ways that are not possible in more conventional environments. For example, the study of black holes in X-ray binaries provides an opportunity to test general relativity in regimes where gravitational forces are incredibly strong. By observing the motion of matter around black holes, scientists can test the predictions of Einstein's theory and search for deviations that might indicate the presence of new physics. Similarly, the study of neutron stars in X-ray binaries allows scientists to probe the behavior of matter under extreme conditions. The density of matter in neutron stars is so high that it exceeds anything that can be achieved in laboratory experiments. This makes neutron stars an ideal laboratory for testing the laws of physics in extreme environments. By studying the behavior of matter in the accretion disk of neutron stars, scientists can learn more about the equation of state of nuclear matter, which describes how matter behaves under the incredibly high pressures found in these objects. As our observational techniques continue to improve, we are gaining a more detailed and nuanced understanding of X-ray binaries. The development of new space-based observatories, such as the upcoming James Webb Space Telescope and the planned X-ray Observatory Athena, will provide unprecedented views of these systems. These instruments will allow scientists to observe X-ray binaries in greater detail than ever before, uncovering new phenomena and providing insights into the behavior of matter in some of the most extreme environments in the universe. In addition to new telescopes, the rise of gravitational wave astronomy is also opening up new possibilities for studying X-ray binaries. As mentioned earlier, gravitational waves are produced by the acceleration of massive objects, such as black holes and neutron stars, and can be detected by observatories like LIGO and Virgo. These observations are offering a new way to study the dynamics of compact objects in X-ray binaries, allowing scientists to probe their behavior in ways that were previously impossible. By combining gravitational wave data with X-ray and radio observations, astronomers can gain a more comprehensive picture of the processes that occur in these systems, and potentially uncover new phenomena that challenge our understanding of physics. The field of X-ray binary research is still in its infancy, and there is much more to discover. Every new observation provides new clues about the behavior of compact objects, the nature of accretion, and the role these systems play in the broader context of galaxy evolution. As we continue to observe and study these systems, we will undoubtedly uncover more mysteries, pushing the boundaries of human knowledge and deepening our understanding of the universe. X-ray binaries offer a unique and exciting window into the most extreme conditions in the cosmos. By studying these systems, we not only gain insights into the physics of black holes, neutron stars, and accretion processes, but we also learn more about the universe's fundamental nature. As technology advances, the future of X-ray binary research holds the promise of even more groundbreaking discoveries that will continue to reshape our understanding of the cosmos. The role of X-ray binaries in our understanding of compact objects goes beyond just astrophysical curiosity. These systems help us piece together some of the most significant puzzles about how the universe works. By observing the radiation emitted from these extreme environments, scientists are not just peering into the behavior of black holes and neutron stars. They are also gaining crucial insights into high-energy physics, stellar evolution, and even the formation and fate of galaxies. What makes X-ray binaries such intriguing objects of study is that they allow us to observe the transition from ordinary stellar objects to some of the most extreme entities in the universe, like black holes and neutron stars. The physics governing these systems is so extreme that it pushes the limits of our current understanding. As scientists continue to study these systems, we can begin to understand how matter behaves under the crushing pressures and intense magnetic fields present in the environment around a black hole or neutron star. These insights are vital for testing theories of gravity and quantum mechanics in ways that are otherwise unattainable. One of the most intriguing questions surrounding X-ray binaries is how these systems can produce such high-energy emissions. It's not just about the sheer amount of energy involved, but also the mechanism that powers the production of X-rays. As material from the companion star spirals into the accretion disk around the compact object, it gets heated to extreme temperatures by the immense gravitational forces at work. In certain situations, the material reaches temperatures so high that it begins to emit radiation in the X-ray part of the electromagnetic spectrum. The process of heating the accretion disk is highly complex, and several factors influence how efficiently it occurs. For one, the mass of the compact object plays a significant role. The larger the mass, the greater the gravitational pull, which leads to higher temperatures in the accretion disk. This is one of the reasons why black holes are so effective at producing X-rays. Their immense mass and gravity create conditions where the material in the accretion disk can reach millions of degrees. The result is an intense output of X-rays that can be detected by space telescopes like NASA's Chandra X-ray Observatory or the European Space Agency's Newton satellite. Another factor influencing the X-ray emission is the presence of a powerful magnetic field. In many X-ray binaries, the compact object, whether it's a black hole or a neutron star, has an incredibly strong magnetic field. This magnetic field can play a crucial role in shaping the behavior of the accretion disk and the resulting X-ray emissions. As material falls toward the compact object, the magnetic field can twist and distort the plasma, accelerating particles to high energies. These energetic particles then emit X-rays as they spiral inward along the magnetic field lines, adding another layer of complexity to the emission processes. X-ray binaries don't just emit X-rays in a steady, predictable manner, they can also undergo dramatic outbursts. These outbursts are often caused by changes in the structure of the accretion disk, where material accumulates more quickly than usual, triggering a burst of X-rays. These bursts can last from hours to weeks and are often observed as sudden increases in brightness. While these events can be exciting for astronomers studying them, they also provide valuable data that can help us understand the dynamic nature of accretion processes. Additionally, X-ray binaries can offer clues about the life cycles of massive stars. The companion star in these systems is often a giant or supergiant star, whose end-of-life behavior is markedly different from smaller stars like our Sun. The matter flowing from the companion star to the compact object can offer insights into the stellar evolution process, helping astronomers understand how massive stars evolve into black holes or neutron stars. The rapid accretion of material from the companion star can also affect the star itself, possibly leading to its eventual destruction or transformation into a white dwarf, neutron star, or even another black hole. The interaction between the black hole or neutron star and its companion star also has broader implications for understanding galactic evolution. The energy released by the compact object during accretion can have a significant effect on the surrounding gas and dust in the galaxy. These emissions can heat up the gas, preventing it from collapsing to form new stars. In this sense, X-ray binaries can be seen as a kind of galactic regulator that influences the rate of star formation in their host galaxies. The feedback mechanism between the compact object and its environment is a subject of intense research, as it helps scientists understand how galaxies evolve over time. Furthermore, X-ray binaries also hold clues about the nature of high-energy astrophysics in general. One of the most exciting developments in recent years is the discovery that some X-ray binaries, especially those involving black holes, can emit powerful relativistic jets. These jets are streams of particles that are ejected from the region around the compact object at nearly the speed of light. These jets can carry enormous amounts of energy across vast distances, and their study helps scientists understand how material can be ejected from a compact object despite the intense gravitational forces at play. The discovery of these relativistic jets has opened up a new frontier in astrophysics, offering us a glimpse into some of the most energetic phenomena in the universe. Additionally, these jets are not just fascinating in their own right, they can also provide us with valuable information about the black hole or neutron star at the heart of the X-ray binary. The shape, size, and speed of the jets can reveal crucial details about the mass and spin of the compact object, as well as the structure of the accretion disk and the magnetic field. This information is essential for understanding the fundamental nature of these mysterious objects and the forces at work within them. The study of X-ray binaries also intersects with the field of gravitational wave astronomy. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as the merging of black holes or neutron stars. By detecting these waves, scientists can gain insights into the behavior of compact objects in X-ray binaries. In particular, the collision or merger of compact objects in X-ray binaries could produce detectable gravitational waves, allowing scientists to study these events in unprecedented detail. The combination of X-ray, radio, and gravitational wave data has the potential to transform our understanding of compact objects and their interactions. By analyzing these different types of radiation, astronomers can build a comprehensive picture of the processes at work in X-ray binaries, revealing the underlying physics of accretion, magnetism, and the formation of relativistic jets. Moreover, the detection of gravitational waves from these systems could provide critical insights into the nature of spacetime itself, challenging our understanding of gravity and pushing the boundaries of modern physics. As our observational capabilities continue to improve, the future of X-ray binary research looks incredibly promising. The development of more advanced space telescopes, such as the upcoming Athena mission, promises to reveal even more about these fascinating systems. Additionally, the growing network of gravitational wave observatories will provide us with new tools to explore the dynamic behavior of compact objects in these systems. With each new discovery, we inch closer to unraveling the mysteries of the most extreme objects in the universe. X-ray binaries not only provide us with a window into the behavior of compact objects but also help us understand the broader processes that shape galaxies and the universe as a whole. These systems are among the most extreme environments known to science, and their study will continue to challenge our understanding of physics and the cosmos for years to come. As we continue to explore the mysteries of X-ray binaries, we are not just uncovering the secrets of black holes and neutron stars. We are pushing the limits of human knowledge and redefining our understanding of the universe. As we push the boundaries of our understanding of X-ray binaries, we begin to explore even deeper layers of their complex nature. These systems are not static, but dynamic and evolving, with various factors influencing their behavior over time. From the intense gravitational forces at play, to the magnetic fields that twist and distort the plasma around them, X-ray binaries present a constantly shifting landscape that requires careful observation and analysis. One of the fundamental questions in astrophysics that X-ray binaries can help us answer is the process by which matter behaves in extreme environments. While we can simulate conditions like those found in X-ray binaries on Earth and particle accelerators, these systems give us the opportunity to observe matter under conditions that are far more extreme than anything we can replicate in a laboratory. The way matter behaves as it is heated to millions of degrees, as it is compressed under intense gravity, and as it is twisted by magnetic fields can reveal crucial information about the fundamental properties of matter itself. The role of magnetic fields in X-ray binaries is especially important. These fields, often several orders of magnitude stronger than anything we experience on Earth, have a profound effect on the accretion process. Magnetic fields can channel the flow of material toward the compact object in a manner that creates jets of particles shooting out from the poles of the object. These jets, often visible in the form of high-energy radiation, provide astronomers with a way to trace the structure of the magnetic fields around compact objects. By studying these jets, and the way they interact with the surrounding environment, we can gain insights into the physics of magnetohydrodynamics, MHD, the study of how magnetic fields interact with electrically charged fluids, and better understand the role of magnetic fields in shaping the behavior of matter under extreme conditions. Interestingly, the magnetic fields in X-ray binaries don't just affect the accretion process itself. They also play a critical role in the formation of X-rays. In systems with a neutron star, the magnetic field can trap the accreted matter at the surface, forming a hot spot that emits intense X-ray radiation. In the case of black holes, the material that falls into the event horizon is accelerated to incredibly high speeds, and the magnetic field helps focus this energy, leading to the creation of powerful X-ray emissions. In both cases, the strength and structure of the magnetic field are critical in determining the types of X-ray radiation produced and the way it is emitted. The process of accretion itself is complex and variable. While we often think of it as a steady, continuous process, it can actually fluctuate on timescales ranging from milliseconds to years. For example, the material that accretes onto the compact object may be piled up in the accretion disk, leading to periodic bursts of radiation. These bursts can occur when the material suddenly collapses in on itself, or when changes in the accretion disk structure allow material to fall rapidly into the compact object. Studying these fluctuations allows scientists to gain insight into the structure and behavior of the accretion disk itself, and by extension, into the physics governing accretion processes more generally. X-ray binaries can also shed light on the life cycles of stars. The companion stars in these systems are typically much more massive than the Sun, and they end their lives in dramatic fashion. These stars can explode as supernovae, leaving behind either a black hole or a neutron star as the remnant of the original stellar core. The process by which this occurs, and the interaction between the compact object and the companion star in the X-ray binary, can teach us a great deal about stellar evolution and the final stages of massive stars. Furthermore, by studying X-ray binaries, astronomers can better understand how different stellar populations contribute to the overall evolution of galaxies. The mass transfer from the companion star to the compact object is another fascinating aspect of X-ray binaries. In many cases, the material that falls from the star is not simply lost to space, but instead forms a dense, swirling accretion disk. This disk is composed of hot gas, dust, and other particles that orbit the compact object, creating complex patterns of motion and interaction. As the material spirals inward, it is compressed and heated by the intense gravitational forces of the compact object. Eventually, this material can fall into the object, where it either adds to the mass of the compact object or is expelled in the form of high-energy radiation, including X-rays. The interaction between the companion star and the compact object is not just a one-way process. The compact object can also exert significant influence on the companion star, stripping away mass from the star and altering its evolution. In some cases, the accretion process can slow down or halt entirely, leading to changes in the star's luminosity and other characteristics. In extreme cases, the companion star may even be torn apart by the gravitational forces of the compact object, a process that can result in the formation of a binary system with two compact objects, either two neutron stars or a neutron star and a black hole. These systems, known as double neutron star binaries or black hole neutron star binaries, are of great interest to astrophysicists because they offer insights into the dynamics of compact object interactions and provide valuable opportunities for gravitational wave detection. The study of X-ray binaries has also led to the development of new technologies and techniques in astronomy. The need to observe high-energy radiation from these systems has pushed the development of advanced telescopes capable of detecting X-rays from space. These space-based observatories, such as NASA's Chandra X-ray Observatory and the European Space Agency's Newton, allow astronomers to gather data from X-ray binaries that would be impossible to detect using ground-based telescopes. The continued advancement of these technologies, along with the development of new detectors and analytical tools, promises to reveal even more about the behavior of these extreme systems. The complexity of X-ray binaries and their associated phenomena has led to the development of sophisticated models and simulations that help us understand the underlying physics. These models incorporate the principles of general relativity, quantum mechanics, and magnetohydrodynamics to describe the behavior of matter in the extreme environments around compact objects. While we have made significant progress in understanding the fundamental processes at play in X-ray binaries, there is still much to learn. Each new discovery adds another piece to the puzzle, bringing us closer to a complete understanding of these fascinating systems. Perhaps one of the most exciting aspects of X-ray binaries is their potential for future discoveries. As our observational tools improve, we will be able to detect X-ray binaries in greater detail and with higher precision. New space missions, such as the upcoming launch of the IXB, Imaging X-ray Polarimetry Explorer, and the Athena mission, promise to provide us with unprecedented views of X-ray binaries, allowing us to study their behavior in ways we never thought possible. With the advent of gravitational wave astronomy, we are also on the brink of discovering more about the interactions between compact objects and how these systems influence the surrounding space-time. Moreover, as our understanding of X-ray binaries deepens, we may uncover entirely new phenomena that challenge our current models of astrophysics. The extreme conditions around black holes and neutron stars, combined with the dynamic interactions between the compact object and its companion, could reveal entirely new aspects of fundamental physics. These discoveries could reshape our understanding of the universe, offering new insights into the nature of gravity, quantum mechanics, and the very fabric of space and time. As we continue to explore the mysteries of X-ray binaries, we are not just learning about the physics of compact objects. We are also gaining a deeper understanding of the universe itself. Each new discovery brings us closer to unlocking the secrets of these extreme systems, helping us to answer some of the most profound questions about the cosmos and our place within it. Whether we are studying the behavior of matter under the influence of intense gravity, observing the formation of relativistic jets, or detecting gravitational waves, X-ray binaries offer us a glimpse into the most extreme environments known to science. In doing so, they open the door to a deeper understanding of the universe, pushing the boundaries of what we know and revealing the hidden mysteries of space. The fascinating thing about X-ray binaries is that they not only teach us about compact objects like black holes and neutron stars, but they also challenge our understanding of time and space itself. Their study is a gateway into one of the most exciting and mysterious realms of astrophysics. When we observe these systems, we're not just watching stars or planets, we're observing the fundamental processes that govern the universe on the most extreme scales. By delving deeper into the mechanics of X-ray binaries, we unlock new ways to think about the fabric of reality and its laws. One of the aspects that make X-ray binaries so intriguing is their variability. These systems don't behave in a predictable, steady way. Instead, their behavior changes over different time scales. Some X-ray binaries exhibit rapid changes, like sudden bursts of X-ray radiation that can last for just seconds or minutes. Others may show more gradual changes over days, weeks, or even months. These fluctuations are a direct result of the complex dynamics occurring in the accretion disk, where material is being pulled in by the compact object. Sometimes, material gets trapped, causing the system to reach a critical point where it suddenly releases an enormous amount of energy. Other times, the material may fall into the compact object in a more continuous, steady manner. This variability, which is so distinctive to X-ray binaries, is not just fascinating for astronomers, it also allows them to study the internal workings of these systems in great detail. By carefully observing how the X-ray radiation changes, scientists can begin to infer the properties of the accretion disk, the compact object, and the surrounding environment. They can also better understand how the matter flows around these objects, and how the immense gravitational forces at play cause such dramatic changes in the system's emissions. One of the most intriguing aspects of this variability is the fact that it often comes in the form of periodic behavior. Some X-ray binaries exhibit periodic outbursts, where the intensity of the X-rays rises and falls at regular intervals. These periodic fluctuations are often linked to the orbital motion of the companion star, as it passes through regions of the accretion disk and interacts with the magnetic fields around the compact object. This type of variability allows scientists to study the mass and structure of the compact object with great precision. For example, by observing the regular timing of these outbursts, scientists can measure the mass of the black hole or neutron star at the center of the system. In some cases, these outbursts can be so powerful that they result in a burst of high-energy radiation that can be detected by telescopes on Earth. These X-ray bursts are often seen in systems with neutron stars, where the material that accretes onto the surface of the neutron star builds up until it suddenly ignites, creating a brief but intense flash of X-ray radiation. These bursts can provide key insights into the structure of neutron stars and how they function. By analyzing the X-ray spectra from these bursts, scientists can learn more about the composition of the neutron star's surface, its magnetic field, and how it behaves under such extreme conditions. Another fascinating element of X-ray binaries is the possibility of gravitational waves. When two compact objects, such as a neutron star and a black hole, orbit each other in a binary system, they create ripples in space-time. These ripples are known as gravitational waves, and they carry information about the masses and motions of the objects involved. Gravitational waves were first predicted by Albert Einstein as part of his general theory of relativity, and in recent years, scientists have been able to directly detect these waves using advanced instruments like LIGO, Laser Interferometer Gravitational Wave Observatory. X-ray binaries, especially those with two compact objects, are prime candidates for producing gravitational waves that are detectable by these instruments. By studying the gravitational waves emitted by these systems, astronomers can learn even more about the properties of black holes, neutron stars, and the environments around them. In fact, some of the first gravitational wave detections came from binary systems containing a neutron star and a black hole, underscoring the importance of X-ray binaries in the broader context of astrophysics. The study of gravitational waves is still in its infancy, and the potential for discovery is vast. With the advancement of gravitational wave observatories, we can expect to gain unprecedented insights into the nature of compact objects and their interactions. These discoveries will not only deepen our understanding of X-ray binaries but could also revolutionize our understanding of the universe as a whole. We could begin to detect gravitational waves from more distant systems, perhaps even those located at the edge of the observable universe, giving us a direct glimpse into the most extreme regions of space. As we continue to study X-ray binaries, the role of advanced technologies and observational techniques cannot be overstated. X-ray astronomy, which involves detecting the X-rays emitted by objects in space, has made tremendous strides in recent decades. Early X-ray telescopes like the Uhuru satellite and the Ariel 4 mission laid the groundwork for future advancements. These early missions identified the first X-ray binaries, revealing the existence of these strange systems and opening up a new field of study. Since then, space-based observatories like NASA's Chandra X-ray Observatory and the European Space Agency's Newton have provided us with more detailed and high-resolution images of X-ray binaries. These telescopes are capable of detecting the high-energy radiation emitted by compact objects and their surrounding accretion disks. The data collected from these missions has allowed scientists to map the structure of X-ray binaries, measure their masses, and study the physical conditions around compact objects in more detail than ever before. In addition to X-ray telescopes, New technologies like gravitational wave detectors are expanding our ability to study these systems in entirely new ways. By combining data from X-ray observatories and gravitational wave detectors, scientists can create a more complete picture of X-ray binaries and their behavior. These combined observations help us understand the complex interplay between different types of radiation, the dynamics of the accretion process, and the properties of the compact objects at the center of these systems. With each new observation, we are learning more about the role that X-ray binaries play in the universe. They are not just isolated systems, they are part of a larger, interconnected cosmic web. The interactions between compact objects and their companions provide us with valuable clues about the processes that govern the formation and evolution of stars, galaxies, and the universe as a whole. By continuing to study these systems, we can better understand the forces that shape the cosmos and how they affect the evolution of the universe over time. X-ray binaries also have implications for our understanding of the life cycle of stars. In many cases, these systems are in their final stages of evolution, with the companion star nearing the end of its life. These massive stars undergo dramatic transformations as they exhaust their fuel, ultimately leading to a supernova explosion. In some cases, the supernova may leave behind a neutron star or black hole, which then becomes part of the X-ray binary system. By studying these systems, we gain a better understanding of the processes that govern stellar death and the formation of compact objects. We can also learn more about the conditions that give rise to different types of compact objects, whether they be black holes, neutron stars, or white dwarfs. These insights are critical to our understanding of stellar evolution and the broader life cycle of stars. Moreover, X-ray binaries have an important role to play in our understanding of the distribution of matter in the universe. These systems are often located in regions of space where there is a high concentration of matter, such as in the cores of galaxies or in binary systems near the galactic plane. By studying X-ray binaries, we can learn more about the way matter is distributed in these regions and how it influences the formation and evolution of galaxies. As technology advances and our observational capabilities improve, the mysteries of X-ray binaries will continue to unfold. New telescopes, new detectors, and new methods of analysis will allow us to gather more data and make new discoveries. The study of these systems is a key area of research in modern astrophysics, and it holds the promise of revealing many of the most fundamental secrets of the universe. X-ray binaries serve as a window into the extreme conditions that govern the universe. They provide us with an opportunity to observe the most intense gravitational, magnetic, and thermal forces in nature. By continuing to explore these systems, we not only deepen our understanding of the universe but also push the boundaries of human knowledge itself. As we unravel the mysteries of these fascinating systems, we come one step closer to answering some of the most profound questions in science. What is the nature of black holes? How do stars evolve? What happens to matter in the most extreme environments of the universe? X-ray binaries are much more than just objects of study. They are a key to unlocking the secrets of the cosmos. And as we continue to explore their mysteries, we may find ourselves at the forefront of some of the most groundbreaking discoveries in astrophysics. The deeper we explore the phenomenon of X-ray binaries, the more we realize just how much they teach us about the intricate dance of gravity, matter, and energy. These systems are not merely a fascinating curiosity. They are essential to our understanding of some of the universe's most fundamental processes. From the immense gravitational pull exerted by compact objects to the extreme temperatures and pressures that allow matter to behave in strange and unexpected ways, X-ray binaries present a perfect storm of cosmic phenomena that defy conventional expectations. What's truly remarkable about X-ray binaries is how they encapsulate the interplay between two very different objects: a compact object, either a black hole or a neutron star, and its companion star. The interaction between the two produces an environment that is, in many ways, more extreme than anything we encounter in the familiar universe. As the compact object pulls in matter from its companion, this material doesn't fall directly into it right away. Instead, it forms an accretion disk, a swirling mass of hot, dense gas that orbits the compact object in a complex and dynamic fashion. This disk becomes incredibly hot due to the friction created as material moves at incredibly high speeds. As it heats up, the gas begins to emit X-rays, and it is these X-rays that astronomers observe when studying these systems. The process through which X-ray radiation is emitted from the accretion disk is an area of intense scientific interest. To understand it fully, we must look at how matter behaves under such extreme conditions. As material from the companion star is stripped away, it spirals inward toward the compact object. As the material accelerates, its temperature rises dramatically, leading to the emission of high-energy radiation, including X-rays. This phenomenon is analogous to a cosmic furnace, where temperatures soar to millions of degrees, far beyond what any human-made machine could achieve. This process also gives us insight into the behavior of spacetime itself. In the vicinity of compact objects, the gravitational pull is so intense that it bends light, warps time, and distorts the very fabric of space. This effect, known as gravitational lensing, causes light from the surrounding accretion disk to follow curved paths, making the system appear different than it would if viewed from a more familiar, non-distorted perspective. The extreme gravitational forces near the compact object cause a region called the event horizon to form in the case of a black hole. This region marks the point beyond which not even light can escape, and the study of X-ray binaries near this threshold helps astronomers probe the nature of black holes in ways that would be otherwise impossible. One of the most groundbreaking discoveries in X-ray binary research involves the precise measurement of black hole masses. By observing the X-ray emissions and the orbital motions of the companion star, astronomers can infer the mass of the black hole in these systems. This method has allowed scientists to measure the masses of several stellar mass black holes with remarkable precision. These measurements are crucial because they provide insight into the formation and growth of black holes, as well as their role in the evolution of galaxies. Another fascinating aspect of X-ray binaries is their potential role in the broader cosmic landscape. The materials in the accretion disk, including hydrogen and helium, are constantly being fed into the compact object. Over time, this accretion process can influence the overall mass and growth of the black hole or neutron star. The gas that is captured can also be expelled in powerful jets that shoot outward from the system at nearly the speed of light. These jets are made up of particles accelerated by the immense magnetic fields around the compact object, and they can stretch for thousands of light years. While these jets may seem like a feature of only the most extreme systems, they are actually more common than we might think, and their study is helping scientists learn about the distribution of matter in the universe. This accretion process can also lead to the production of some of the most powerful explosions in the universe. In systems with neutron stars, for example, when the accretion process becomes especially intense, the material on the surface of the neutron star can ignite in a violent explosion. This results in what is known as a type I X-ray burst. These bursts are short, intense flashes of X-rays that can last for just seconds to minutes. These events are a direct consequence of the incredible pressures and temperatures at work in these systems, and they provide valuable information about the physics of neutron stars, including their interior structure and how they handle immense gravitational forces. Perhaps even more interesting is the fact that these systems have the potential to teach us about the very nature of matter at its most fundamental level. The extreme conditions in X-ray binaries, including the crushing gravity near black holes and neutron stars, give us a rare glimpse into how matter behaves under pressures and temperatures that can't be replicated in laboratories here on Earth. This allows scientists to test theories of physics in new and extreme environments. For example, some scientists hope that by studying the X-ray emissions from these systems, they can learn more about the state of matter in the cores of neutron stars, which could help us unlock the mystery of nuclear matter, matter in a form that only exists under extraordinary conditions. The study of X-ray binaries also challenges our understanding of the nature of time. The intense gravitational fields around compact objects warp spacetime, meaning that time flows differently for observers in these regions compared to those further away. This effect, predicted by Einstein's theory of relativity, is most noticeable near black holes. As the companion star orbits the black hole, its movements are altered by the warped spacetime around it. In extreme cases, the gravitational pull of the black hole can even cause time dilation, where time appears to move slower near the black hole for an observer in a distant location. This is one of the most mind-bending effects of the universe, and it underscores just how much our intuitions about time and space can be challenged when dealing with the most extreme environments. Additionally, the extreme conditions within X-ray binaries can lead to some unusual phenomena, such as spaghettification, the process by which objects are stretched and pulled apart by the tidal forces near a black hole. If a star or planet ventures too close to the event horizon, it will be torn apart as it is drawn in, a process that produces intense radiation and further contributes to the X-ray emissions we observe. The material from these objects is then incorporated into the accretion disk, adding to the swirling mass of matter that surrounds the black hole or neutron star. In the case of black hole X-ray binaries, we are also learning about the so-called inner workings of black holes. When matter gets close to a black hole, it heats up and begins to emit intense X-rays. The region just outside the event horizon of a black hole is a place where matter behaves in strange ways. The energy that is released here is so intense that it affects the surrounding space-time itself. By observing these high-energy X-rays, scientists can gain a better understanding of how matter behaves as it approaches the event horizon and how black holes interact with their surroundings. This research is helping to reveal the inner mysteries of black holes, which remain one of the most enigmatic and elusive objects in the universe. The study of X-ray binaries has far-reaching implications not just for astronomy, but also for our understanding of the universe's very origin and ultimate fate. These systems can help us understand the process of stellar evolution, the formation of compact objects, and the dynamic interactions between stars and their environments. By studying how matter behaves in these extreme environments, we gain valuable insights into the fundamental forces that govern the cosmos. Furthermore, X-ray binaries have the potential to provide us with answers to some of the most profound questions in astrophysics. For instance, how do black holes grow and evolve? What role do they play in galaxy formation and evolution? How does the accretion process influence the dynamics of galaxies and the distribution of matter in the universe? These questions are not just academic. They have practical implications for our understanding of the larger-scale structure and evolution of the universe. In many ways, the study of X-ray binaries is just beginning. As technology continues to advance, and as we develop better observational tools, the mysteries surrounding these fascinating systems will only deepen. New space telescopes, more sensitive detectors, and more advanced computational techniques will allow us to observe these systems in greater detail, uncovering new layers of complexity and revealing phenomena that were once beyond our reach. X-ray binaries are far from just being scientific curiosities. They are a window into the extreme processes that govern the universe, providing us with unique insights into the nature of matter, gravity, and energy. Their study challenges our understanding of the universe, pushing the boundaries of knowledge and revealing the hidden forces at work in the most extreme corners of the cosmos. As we continue to study these systems, we will undoubtedly make new discoveries that will revolutionize our understanding of the universe, deepening our appreciation for the complexity and beauty of the cosmos. X-ray binaries are an extraordinary frontier in astrophysics that merge multiple fields of scientific inquiry, ranging from the nature of gravity to the fundamental properties of matter under extreme conditions. These systems are not just fascinating because they reveal the fundamental physics of black holes and neutron stars, but also because they show us the processes by which stellar objects interact and evolve. Each new observation offers a piece of the puzzle, and the more we understand these systems, the more we realize how much remains to be discovered. One area where X-ray binaries have a profound impact is in the study of the fundamental forces of the universe. When we think of the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, X-ray binaries provide us with a natural laboratory to test these forces. The extreme gravitational fields around black holes and neutron stars stretch and warp space-time, allowing us to observe the behavior of these forces in ways that cannot be replicated in the lab. The matter in these systems is subjected to forces that are impossible to replicate on Earth. When a black hole pulls material from a companion star, this material is often compressed to incredibly high densities and heated to temperatures exceeding millions of degrees. The physical properties of this matter behave in ways that are entirely unfamiliar. We are able to study these high-energy processes in real time, gaining new insights into the interactions between matter and energy under extreme conditions. In the case of neutron stars, the matter found in their interiors, composed largely of neutrons, behaves in ways that challenge our current understanding of nuclear physics. One of the great advances in the study of X-ray binaries is how they have helped to improve our understanding of how black holes are formed and how they interact with their environments. There is still much debate over the exact mechanism by which stellar black holes form, but the study of X-ray binaries has provided valuable clues. For instance, by observing how the companion star behaves as it loses mass to the black hole, astronomers have been able to infer key properties of the black hole itself, including its mass and spin. This information has been crucial for understanding how black holes grow and evolve over time. The discovery of intermediate mass black holes, those whose mass lies between stellar mass black holes and supermassive black holes, has also been aided by X-ray binaries. These black holes are notoriously difficult to detect, but their presence can be inferred by the behavior of the companion star in an X-ray binary system. The key to identifying these elusive objects lies in observing the gravitational effects they exert on the companion star. This has opened up new possibilities for exploring the intermediate mass range, providing a link between the stellar mass and supermassive black holes that dominate the centers of galaxies. Another fascinating aspect of X-ray binaries is their potential connection to gravitational waves. Gravitational waves are ripples in space-time caused by massive objects accelerating through space, and their detection has opened up a new era of observational astrophysics. It is believed that some X-ray binaries could be sources of gravitational waves, particularly those where a neutron star or black hole is in close orbit with its companion. The collision or merger of these objects could produce gravitational waves detectable by the next generation of observatories. This would allow us to not only study the properties of compact objects like black holes and neutron stars, but also to gain new insights into the nature of spacetime itself. X-ray binaries have also provided insights into the dynamics of accretion processes and their impact on the surrounding environment. The accretion disk around a black hole or neutron star is not a static object. It is a complex, dynamic system that changes over time. For example, changes in the rate at which matter is being accreted can cause fluctuations in the X-ray emissions, providing astronomers with a means of studying the behavior of the accretion process in real time. This has helped to refine our models of how matter flows in and around compact objects, and has provided evidence for processes like the launching of relativistic jets. One of the most fascinating aspects of these systems is the role that magnetic fields play in the dynamics of the accretion disk. In both black holes and neutron stars, magnetic fields can exert a powerful influence on the behavior of the surrounding matter. Magnetic fields can channel the flow of material in and out of the accretion disk, leading to the formation of relativistic jets of particles that shoot out from the poles of the compact object. These jets are not only a fascinating feature of X-ray binaries, but they also play a critical role in the evolution of galaxies. In some cases, the material in the jets can be ejected with such energy that it may eventually interact with the surrounding interstellar medium, influencing the formation of stars and the evolution of galaxies. While much of the focus in the study of X-ray binaries has been on black holes and neutron stars, these systems are also valuable for understanding the properties of normal stars, particularly the companion stars. By studying the way in which a companion star loses mass to a black hole or neutron star, astronomers can learn about the internal structure of the star itself. The companion star may be stripped of its outer layers, exposing its core and providing valuable information about stellar evolution and the life cycles of stars. In addition to their direct impact on our understanding of stellar evolution, X-ray binaries also serve as a reminder of the dynamic nature of the universe. These systems are not static, they evolve over time. Some X-ray binaries are in the process of merging, while others may eventually evolve into systems that produce supernovae, or even gamma-ray bursts. This evolution, driven by the complex interactions between the compact object and its companion, is one of the many ways in which the universe continues to surprise and challenge us. Beyond the technical aspects, the study of X-ray binaries offers a philosophical insight into the nature of the universe. The fact that such extreme phenomena exist, where matter is compressed to densities beyond anything we can fathom, and energy is released in bursts that outshine entire galaxies, speaks to the richness and complexity of the cosmos. It is a humbling reminder that the universe operates on scales and in ways that we can barely comprehend. As we continue to study X-ray binaries, we not only learn about the nature of black holes, neutron stars, and their companions, but also come closer to understanding the broader questions of why the universe is the way it is. In the grand scheme of astrophysical research, X-ray binaries hold a special place. They are cosmic laboratories where we can study the most extreme conditions imaginable, from the crushing gravity of black holes to the unimaginable pressures in the cores of neutron stars. They challenge our understanding of physics, inspire new theoretical models, and provide us with some of the most dramatic and awe-inspiring phenomena in the universe. And as our observational tools continue to improve, there is little doubt that X-ray binaries will continue to provide us with new discoveries that push the boundaries of human knowledge. So, the next time you gaze up at the night sky, remember that within that vast expanse, there are systems, X-ray binaries, that defy imagination and offer us a glimpse into the most extreme and exotic environments in the universe. As we continue to peel back the layers of these systems, one question remains at the forefront of our minds: what other cosmic mysteries are still waiting to be uncovered? As we peer deeper into the heart of X-ray binaries, we begin to understand not only the mechanics of these systems, but also how they serve as a unique testbed for the fundamental principles of physics. The observation of these cosmic phenomena allows us to challenge our most basic assumptions about how matter behaves, especially under extreme conditions that cannot be replicated on Earth. The forces at play in X-ray binaries are the product of gravity, magnetism, and intense radiation, interacting in ways that no human-made experiment can fully mimic. At the heart of these systems lies the compact object, which, whether a black hole or a neutron star, behaves like a cosmic engine, pulling in vast amounts of matter from its companion star. This process, known as accretion, is where the real magic of X-ray binaries happens. The accretion disk, a swirling mass of gas and dust that spirals inward toward the compact object, becomes incredibly hot as it is compressed under intense gravity. The matter within the disk reaches temperatures of millions of degrees Celsius, emitting X-rays that can be detected by space telescopes like NASA's Chandra X-ray Observatory or the European Space Agency's Newton. The X-rays emitted from these accretion disks provide us with detailed information about the structure and dynamics of the binary system. By analyzing the spectrum of X-rays, scientists can discern the mass of the black hole or neutron star, the spin of the compact object, and the nature of the accretion process itself. In particular, the X-ray emissions tell us about the temperature and density of the accretion disk, and the way in which this disk changes as it nears the compact object. One of the most exciting aspects of studying X-ray binaries is the way in which these systems allow us to probe the properties of black holes and neutron stars. Black holes, by their very nature, do not emit light directly, so detecting them can be incredibly challenging. However, in an X-ray binary, the presence of a black hole can be inferred by the way it interacts with its companion star. The black hole's intense gravity distorts the space around it, causing the companion star's orbit to behave in ways that reveal the mass of the black hole. By studying these orbits, scientists can precisely measure the mass of the black hole, providing us with important clues about how these enigmatic objects form and evolve. Neutron stars, on the other hand, are incredibly dense objects that are formed when massive stars exhaust their fuel and collapse under their own gravity. These stars are only about 1.4 times the mass of the Sun, yet they are compressed into a sphere the size of a city. The material that makes up a neutron star is in a state that is far beyond what we experience in our daily lives. The neutrons that make up the star are packed so tightly that they create a gravitational field strong enough to warp space-time itself. When matter from the companion star falls onto a neutron star, it generates intense X-ray radiation, and the behavior of this radiation helps astronomers understand the neutron star's internal structure. In addition to their role in studying compact objects, X-ray binaries are also crucial for understanding the broader processes that govern the evolution of stars and galaxies. The material stripped from the companion star often does not simply fall into the compact object. Instead, it forms a powerful jet of particles that can extend far beyond the binary system. These jets are made up of highly energetic particles that travel at nearly the speed of light. As they interact with the surrounding gas and dust, the jets release enormous amounts of energy, which can influence the dynamics of the entire galaxy. This process of accretion and ejection not only shapes the environment around the binary system but also plays a role in the feedback mechanisms that govern the formation and evolution of galaxies. The energy released by the jets can heat up the surrounding gas, preventing it from collapsing to form new stars. In this way, X-ray binaries help to regulate the rate of star formation within galaxies. This feedback loop between the compact objects and their environments provides critical insights into the life cycle of galaxies and the role of black holes and neutron stars in galactic evolution. Another important area of research in X-ray binaries is the study of the magnetic fields associated with neutron stars and black holes. Both of these compact objects can have extremely powerful magnetic fields, which exert a profound influence on the surrounding material. For neutron stars, the magnetic field is often so strong that it can direct the flow of material in the accretion disk, leading to the formation of beams of radiation that emit from the poles of the star. These beams are responsible for the characteristic pulsations observed in some neutron stars, known as pulsars. In black hole systems, the magnetic field is even more mysterious. The magnetic field of a black hole is believed to play a critical role in the formation of relativistic jets, which are streams of particles that shoot away from the poles of the black hole at nearly the speed of light. These jets are one of the most striking features of X-ray binaries and can be seen in a wide range of wavelengths, from X-rays to radio waves. The exact mechanisms behind the formation of these jets are still not fully understood, but they represent an active area of research, and their study could reveal new insights into the nature of black holes and the physics of extreme environments. X-ray binaries also provide valuable clues about the evolution of stars. These systems are not static. They change over time as the stars evolve. The companion star, which is usually a massive star that has exhausted its nuclear fuel, may eventually become a white dwarf, neutron star, or black hole. In some cases, the accretion process itself can cause the companion star to evolve in ways that are not seen in isolated stars. For example, the material flowing from the companion star can trigger new nuclear reactions, altering the star's composition and internal structure. Over time, the accretion process can alter the orbit of the companion star, bringing it closer to the compact object. This may lead to the eventual merger of the two stars, an event that can produce spectacular phenomena like supernovae or gamma-ray bursts. These events can have profound consequences for the surrounding environment, including the ejection of material into space, which can contribute to the formation of new stars and planets. The study of X-ray binaries is also tied to some of the most profound questions in physics. For example, these systems allow us to test theories of general relativity in the most extreme environments possible. The intense gravitational fields around black holes and neutron stars distort spacetime in ways that can be measured and studied. Observations of these systems have already provided some of the most compelling evidence for the existence of black holes, and they continue to push the boundaries of our understanding of how gravity operates. In recent years, the discovery of gravitational waves, ripples in spacetime caused by massive objects accelerating through space, has opened up an entirely new frontier in the study of X-ray binaries. These systems may be responsible for some of the gravitational waves detected by observatories like LIGO and Virgo. When two compact objects in an X-ray binary system collide or merge, they can generate powerful gravitational waves that travel across the universe, carrying information about the properties of the objects involved. The study of these waves is still in its early stages, but it holds the potential to revolutionize our understanding of the universe and the behavior of matter in extreme conditions. X-ray binaries are truly remarkable systems. They are at the intersection of several fields of astrophysics, providing insights into everything from stellar evolution to the nature of gravity itself. As we continue to observe and study these systems, we will undoubtedly uncover more mysteries that will challenge our understanding of the universe. The more we learn about these systems, the more we realize how much is still to be discovered. X-ray binaries are a testament to the complexity and wonder of the universe. They are a reminder that the cosmos is full of strange and beautiful phenomena, and that even in the most extreme and violent environments, there is still much to learn. With each new observation, we come one step closer to understanding the fundamental forces that govern the universe and the nature of the objects that inhabit it. As we continue our exploration of X-ray binaries, it becomes clear that these systems not only challenge our understanding of fundamental physics, but also open the door to new possibilities in our quest to understand the universe. The very nature of X-ray binaries, with their blend of extreme gravity, intense radiation, and the interplay between compact objects and their companion stars, provides a unique vantage point to study phenomena that would otherwise be impossible to observe. One of the most intriguing aspects of X-ray binaries is their role in providing insights into the behavior of matter under extreme conditions. These systems are laboratories for studying the effects of high-energy radiation and strong gravitational fields on matter. As matter spirals into the compact object at the center of the binary, it undergoes violent transformations, reaching temperatures and densities that far exceed anything we can replicate on Earth. In these environments, matter behaves in ways that challenge our understanding of physics, particularly in the realms of quantum mechanics and general relativity. For instance, the behavior of the material in the accretion disk near a black hole or neutron star provides a natural test for the predictions of general relativity. The intense gravitational field near a compact object causes spacetime to warp, and this warping affects the motion of matter in the accretion disk. By observing how light from this disk is bent, distorted, or redshifted, scientists can measure the strength of the gravitational field and test Einstein's theories in ways that are not possible with less extreme objects. These tests are essential for confirming or challenging our current models of gravity and the fundamental nature of space and time. Moreover, the study of X-ray binaries has led to the discovery of exotic phenomena such as relativistic jets, which are streams of particles that travel at nearly the speed of light. These jets, which are often seen emanating from the poles of black holes, are a key feature of many X-ray binaries. The mechanism behind the formation of these jets is still a subject of intense research, but they are believed to be driven by the intense magnetic fields that surround the compact objects. The material in the accretion disk becomes magnetized, and in some cases, the magnetic field lines become twisted and focused into powerful jets. These jets can carry vast amounts of energy, traveling across vast distances and sometimes even reaching beyond the host galaxy. The study of these jets not only helps us understand the behavior of matter in extreme conditions but also provides insights into the processes that govern the formation and evolution of galaxies. Another fascinating aspect of X-ray binaries is the way in which they interact with their surroundings. As the compact object accretes matter from its companion star, it can produce intense radiation that influences the gas and dust in the surrounding space. This radiation can heat up nearby material, causing it to glow and emit light in a variety of wavelengths, from X-rays to visible light. In some cases, the radiation from the binary system can even trigger the formation of new stars by compressing nearby gas clouds. This process, known as triggered star formation, is thought to play a role in the evolution of galaxies. The energy produced by X-ray binaries can also drive large-scale outflows of gas, which can prevent the formation of new stars and regulate the growth of galaxies. X-ray binaries also provide valuable information about the life cycles of stars. These systems are often made up of a massive star that is nearing the end of its life, and the process of accreting matter from its companion star can cause it to evolve in unexpected ways. For example, the material flowing from the companion star can trigger new nuclear reactions in the core of the star, changing its chemical composition and structure. This can result in the star transforming into a white dwarf, neutron star, or even a black hole. The evolution of the companion star in an X-ray binary provides a unique perspective on the end stages of stellar life and the various pathways that stars can take as they reach the end of their existence. Over time, X-ray binaries can evolve and change, sometimes leading to dramatic events such as supernova explosions or the merger of two compact objects. In some cases, the accretion of matter from the companion star can cause the compact object to grow in mass, eventually reaching a critical threshold that leads to a cataclysmic event. For example, if two compact objects in a binary system are in close enough proximity, their mutual gravitational attraction can cause them to spiral inward and eventually merge, releasing an enormous amount of energy in the form of gravitational waves and electromagnetic radiation. These events, known as binary mergers, are some of the most powerful phenomena in the universe, and the study of these events is a key area of research in both observational astronomy and theoretical astrophysics. The discovery of gravitational waves, which are ripples in spacetime caused by the acceleration of massive objects, has added a new layer of complexity to our understanding of X-ray binaries. When two compact objects in an X-ray binary system merge, they generate gravitational waves that travel across the universe, carrying information about the masses, spins, and orbital dynamics of the objects involved. These waves can be detected by observatories such as LIGO and Virgo, and the study of these signals is helping scientists gain new insights into the properties of compact objects and the fundamental nature of gravity. Gravitational wave astronomy is still in its early stages, but it has the potential to revolutionize our understanding of X-ray binaries and the universe as a whole. The role of X-ray binaries in shaping the universe is also significant when we consider their influence on the environments in which they reside. The energy released by these systems can have a profound impact on the surrounding interstellar medium, affecting the distribution of gas and dust in the galaxy. The outflows and jets produced by X-ray binaries can help to regulate the rate of star formation in their host galaxies, either by triggering star formation or by preventing it through the removal of gas. This feedback mechanism plays a key role in the evolution of galaxies and is an important factor in the study of galaxy formation and evolution. In the broader context of astrophysical research, X-ray binaries are often seen as the laboratories for testing theories of high-energy physics. These systems, with their extreme conditions, offer a unique opportunity to study how matter behaves under the influence of intense gravity, radiation, and magnetic fields. The study of X-ray binaries has already led to numerous breakthroughs in our understanding of the universe, and it is likely that these systems will continue to provide valuable insights into the fundamental laws of physics for years to come. As we continue to observe and study X-ray binaries, we are reminded of the vastness and complexity of the universe. These systems, which are often located millions or even billions of light-years away, represent the extreme limits of physics and offer a glimpse into the forces that shape the cosmos. With each new discovery, we come closer to unlocking the secrets of these fascinating objects and the role they play in the larger cosmic tapestry. The study of X-ray binaries is far from over, and with new telescopes, advanced technologies, and innovative research techniques, we can expect to uncover even more about these enigmatic systems in the years to come. X-ray binaries are truly one of the most captivating and profound phenomena in the universe. Their study provides not only a deeper understanding of the fundamental nature of matter and energy but also sheds light on the processes that govern the evolution of stars, galaxies, and the universe as a whole. These cosmic systems challenge our current understanding of physics, pushing the boundaries of what we know and forcing us to confront the mysteries that lie at the heart of the cosmos. As we continue to explore the fascinating world of X-ray binaries, one of the most intriguing aspects is the role that these systems play in the broader cosmic environment. Their study not only deepens our understanding of stellar evolution and the behavior of matter under extreme conditions but also helps us understand the larger-scale dynamics of galaxies and the universe itself. One area where X-ray binaries provide crucial insight is in the understanding of the life cycle of stars. In many cases, these systems involve a massive star at the end of its life, transferring material to a compact object such as a black hole or neutron star. This interaction significantly alters the fate of both the donor star and the compact object. Over time, the accretion of matter from the companion star can change the structure and composition of the compact object, potentially leading to its growth and eventual transformation into a more massive black hole or neutron star. This process offers a glimpse into the final stages of stellar life and the eventual evolution of compact objects. The evolution of X-ray binaries is often closely tied to the broader evolution of galaxies. In particular, the energy and radiation emitted by these systems can have a profound impact on the interstellar medium, the gas and dust that make up the bulk of a galaxy's matter. The high-energy radiation and powerful jets produced by the compact objects in X-ray binaries can heat and ionize nearby gas, triggering or inhibiting star formation. In some cases, the energy released by X-ray binaries can even push large amounts of gas out of the galaxy, affecting the overall growth and evolution of the galaxy. This feedback mechanism, where the energy output of X-ray binaries influences the formation of new stars, is a key element in the study of galactic evolution. In addition to their role in galactic evolution, X-ray binaries also offer a unique laboratory for testing the fundamental principles of physics. The extreme conditions found in these systems, such as the intense gravitational fields around black holes and neutron stars, provide an opportunity to study phenomena that are impossible to replicate in the laboratory. For instance, the intense gravity near a black hole warps spacetime in ways that cannot be observed anywhere else. By observing how light behaves as it passes near these massive objects, scientists can test the predictions of general relativity and gain a deeper understanding of the nature of gravity. The study of X-ray binaries also plays an important role in our quest to understand the fundamental forces that govern the universe. The interplay between matter and radiation in these systems provides a natural laboratory for studying high-energy processes that involve both general relativity and quantum mechanics. This intersection of two of the most important theories in physics, Einstein's theory of general relativity and quantum field theory, is still not fully understood, and the study of X-ray binaries may provide important clues to resolve this mystery. The way in which the intense gravitational fields near a black hole or neutron star affect the behavior of matter could help scientists bridge the gap between these two seemingly incompatible theories. One of the most exciting recent developments in the study of X-ray binaries is the discovery of gravitational waves. Gravitational waves are ripples in the fabric of spacetime that are produced by the acceleration of massive objects. These waves can be detected by sensitive instruments like LIGO and Virgo, and they provide a new way to study the universe. When two compact objects, such as a black hole and a neutron star, merge, they create powerful gravitational waves that carry information about the masses, spins, and other properties of the objects involved. By studying these waves, scientists can gain insights into the nature of compact objects and the behavior of matter in extreme conditions. The detection of gravitational waves from X-ray binary systems is one of the most promising areas of current research, and it is expected to yield groundbreaking results in the years to come. The combination of electromagnetic observations, such as X-ray emissions, and gravitational wave detections allows scientists to study X-ray binaries in a way that was previously impossible. By observing both the light and the gravitational waves emitted by these systems, researchers can gain a more complete picture of the physics involved. This multi-messenger approach to astronomy is a rapidly growing field, and it promises to provide new insights into the nature of X-ray binaries and other extreme astrophysical phenomena. In addition to the breakthroughs in gravitational wave astronomy, the study of X-ray binaries also benefits from the development of more advanced telescopes and observation techniques. Space-based observatories such as the Chandra X-ray Observatory and the XMM Newton satellite provide high-resolution images and spectra of X-ray binaries, allowing scientists to study the behavior of matter in these systems with unprecedented detail. Ground-based observatories, such as the Very Large Telescope, VLT, and the upcoming James Webb Space Telescope, also contribute valuable data that helps us understand the complex physics of these systems. The combination of these observational tools is helping to create a more complete picture of X-ray binaries, from their formation and evolution to the extreme physics that govern their behavior. X-ray binaries also offer insights into the processes that govern the formation and evolution of black holes and neutron stars. By studying the interactions between compact objects and their companion stars, scientists can gain a better understanding of how these objects form, grow, and evolve over time. In particular, the The study of X-ray binaries is helping to refine our understanding of the different types of black holes, including stellar mass black holes, intermediate mass black holes, and supermassive black holes. The processes that govern the formation of these objects are still not fully understood, and X-ray binaries provide a unique laboratory for investigating these mysteries. In the case of neutron stars, the study of X-ray binaries also helps scientists probe the extreme conditions found in the interiors of these objects. Neutron stars are incredibly dense, with matter packed into a small volume, leading to exotic states of matter that are not found anywhere else in the universe. The study of the X-ray emissions from these systems provides valuable information about the structure and composition of neutron stars and helps scientists understand the forces at work inside them. Neutron stars are also thought to be the source of some of the most intense phenomena in the universe, such as gamma-ray bursts, and studying their behavior in X-ray binaries can help us better understand these events. X-ray binaries also play an important role in our understanding of the evolution of galaxies. These systems are often found in star-forming regions of galaxies, where they provide valuable clues about the processes that drive star formation. The energy and radiation emitted by X-ray binaries can influence the surrounding gas and dust, either triggering or inhibiting the formation of new stars. In some cases, the energy released by X-ray binaries can even push gas out of the galaxy, helping to regulate the rate of star formation in the host galaxy. This feedback mechanism is an important aspect of galaxy evolution and is a key area of research in modern astrophysics. X-ray binaries are some of the most fascinating and complex systems in the universe. They serve as natural laboratories for studying the extreme physics of black holes, neutron stars, and the behavior of matter in strong gravitational fields. These systems offer valuable insights into the life cycle of stars, the formation of compact objects, and the processes that govern the evolution of galaxies. As our observational tools and theoretical models continue to improve, we can expect to learn even more about these mysterious systems and the role they play in the broader cosmic landscape. The study of X-ray binaries not only challenges our current understanding of physics, but also opens up new avenues for exploring the deepest mysteries of the universe. As the study of X-ray binaries continues to unfold, one of the most intriguing areas of investigation is the role that these systems play in the larger context of cosmic evolution. X-ray binaries are not isolated phenomena. They are intricately tied to the broader processes that shape the galaxies they inhabit, as well as the overall structure of the universe. As we delve deeper into the science of these systems, it becomes clear that their study provides key insights into the evolution of matter, the formation of compact objects, and the dynamic processes that influence the birth and death of stars. A particularly fascinating aspect of X-ray binaries is their role in the study of stellar remnant formation. The way in which a star reaches its ultimate end state is profoundly influenced by its mass and the environment in which it exists. When a massive star explodes as a supernova, it can leave behind either a neutron star or a black hole, depending on the core mass. This process has been observed in various X-ray binaries, where the compact object, either a neutron star or black hole, feeds on material from a companion star. In these systems, the companion star's mass and structure can significantly affect the evolution of the compact object, as well as the type of remnant it will become. For instance, when a massive star becomes a black hole in a high-mass X-ray binary system, it can begin to accrete material from its companion star. This material forms an accretion disk that spirals into the black hole, emitting X-rays as it is heated to extreme temperatures. The gravitational pull of the black hole is so intense that it warps spacetime, causing the surrounding environment to behave in ways that cannot be replicated under normal conditions. By studying these processes in X-ray binaries, scientists can gain insight into how black holes grow, how matter behaves near these objects, and how they influence the environment around them. Similarly, in low-mass X-ray binaries, where a neutron star serves as the compact object, the accretion of material from a companion star can provide crucial information about the state of matter under extreme pressure and density. Neutron stars are some of the densest objects in the universe, and the matter within them is in an exotic state. The study of these systems allows scientists to probe the interiors of neutron stars, which may hold the key to understanding the nature of matter at its most extreme. The study of X-ray binaries also provides valuable insights into the formation of black holes and neutron stars. While we know that these objects form from the collapse of massive stars, the exact mechanisms of their formation remain unclear. By observing X-ray binaries, scientists can track the evolution of these compact objects as they interact with their companion stars, gaining important clues about how they grow and evolve over time. In particular, the accretion process plays a central role in the evolution of black holes and neutron stars. By studying the way in which material is transferred from the companion star to the compact object, scientists can learn more about the conditions that lead to the formation of these enigmatic objects. Moreover, X-ray binaries serve as laboratories for studying the fundamental forces of nature. The intense gravitational fields near black holes and neutron stars create environments where the laws of physics are pushed to their limits. For example, the immense gravitational pull of a black hole can bend light, stretching and distorting it in ways that challenge our understanding of space and time. This warping of space-time is a direct consequence of Einstein's theory of general relativity, which predicts that gravity has the power to curve the fabric of space-time itself. By observing the behavior of light and matter in these systems, scientists can test the predictions of general relativity and deepen their understanding of how gravity operates under extreme conditions. X-ray binaries also offer unique opportunities for studying high-energy astrophysics. The process of accretion, in which matter is drawn toward the compact object, produces tremendous amounts of energy in the form of X-rays, gamma rays, and other high-energy radiation. By studying this radiation, scientists can learn about the physical processes that govern accretion, including how energy is transferred between the accretion disk and the compact object. This research provides valuable insights into the dynamics of hot, dense matter, and how it interacts with the extreme environments of black holes and neutron stars. Another important aspect of X-ray binaries is their role in the broader structure of galaxies. The energy released by these systems can have a profound impact on the interstellar medium, the gas and dust that permeate galaxies. In particular, the high-energy radiation from X-ray binaries can ionize nearby gas, triggering the formation of new stars. On the other hand, the intense radiation and powerful outflows from the compact object can heat and expel gas, inhibiting star formation. This feedback process can have far-reaching effects on the evolution of galaxies, influencing their size, shape, and star formation rate. By studying X-ray binaries in different types of galaxies, scientists can gain insight into the complex interactions that shape the evolution of galaxies over cosmic time. X-ray binaries also help us understand the interplay between different types of compact objects, particularly in systems where both black holes and neutron stars are present. In some cases, two compact objects, a black hole and a neutron star, can form a binary system. The interactions between these objects can result in unique phenomena, including the emission of gravitational waves and the creation of powerful jets. These systems provide a natural laboratory for studying the dynamics of compact objects and their interactions, offering a unique opportunity to test the predictions of general relativity and other theories of gravity. One of the most exciting areas of research in X-ray binaries is the study of gravitational waves. These ripples in space-time, predicted by Einstein's theory of general relativity, are generated by the acceleration of massive objects, such as black holes and neutron stars. When two compact objects merge, they produce gravitational waves that carry information about the masses, spins, and other properties of the objects involved. By detecting these waves, scientists can gain insights into the nature of compact objects and the processes that govern their formation and evolution. The detection of gravitational waves from X-ray binary systems is a rapidly growing field, and it is expected to provide a wealth of new information about the universe's most extreme phenomena. The future of X-ray binary research is bright, as advances in observational technology and computational models continue to push the boundaries of our understanding. The next generation of space-based telescopes, such as the James Webb Space Telescope and the Athena X-ray Observatory, will provide unprecedented views of X-ray binaries, allowing scientists to study these systems in more detail than ever before. These observatories will also play a crucial role in the search for gravitational waves, offering new opportunities to study the universe's most violent and energetic events. In addition to these technological advancements, the growing field of multi-messenger astronomy is revolutionizing the way scientists study X-ray binaries. By combining data from electromagnetic observations, such as X-ray emissions, with gravitational wave detections, scientists can gain a more complete understanding of these systems. This multi-messenger approach provides a powerful new tool for investigating the physics of black holes, neutron stars, and other compact objects, and it is expected to lead to groundbreaking discoveries in the coming years. X-ray binaries are among the most fascinating and enigmatic systems in the universe. They serve as natural laboratories for studying the extreme physics of compact objects, the formation and evolution of stars, and the dynamics of galaxies. By observing these systems, scientists can gain valuable insights into the fundamental processes that govern the universe, from the behavior of matter under extreme conditions to the nature of gravity itself. As our understanding of these systems continues to grow, X-ray binaries will undoubtedly remain at the forefront of astrophysical research, offering new clues about the most mysterious and powerful phenomena in the cosmos. X-ray binaries remain one of the most powerful sources of information when it comes to the study of high-energy astrophysics. Their combination of compact objects like black holes or neutron stars, together with the accretion of matter from a companion star, creates a dynamic and energetic environment. These systems allow scientists to study the behavior of matter under extreme conditions that are impossible to replicate on Earth. The high temperatures and pressures within the accretion disks lead to the emission of X-rays, providing a direct window into the internal workings of these compact objects. One of the most exciting developments in the study of X-ray binaries is the discovery of new systems. With the advent of more sensitive and powerful telescopes, such as the Chandra X-ray Observatory and the XMM Newton satellite, astronomers have been able to detect X-ray binaries in galaxies far beyond the Milky Way. These discoveries not only expand our understanding of the types of objects that can form in different environments, but also provide insight into the large-scale distribution of compact objects throughout the universe. As we study these systems, we learn more about the nature of the black holes and neutron stars themselves. For instance, black holes have long been a source of fascination due to their mysterious and seemingly paradoxical nature. Their event horizon, the boundary beyond which not even light can escape, is a point of no return. Once matter crosses this threshold, it is thought to be lost forever. However, the material that is accreted by the black hole doesn't simply vanish. Instead, it forms an accretion disk around the black hole, emitting X-rays as it heats up under intense gravitational pressure. These X-rays, detectable by our telescopes, provide an indirect way of studying the black hole's properties, even though the black hole itself cannot be observed directly. Similarly, neutron stars are fascinating objects in their own right. These dense remnants of massive stars are so compact that a single cubic centimeter of a neutron star weighs about as much as a mountain. The physics of neutron stars is still not fully understood, but one of the key features of these objects is their strong magnetic fields, which can be billions of times stronger than Earth's magnetic field. These magnetic fields play a significant role in shaping the behavior of the accretion process in X-ray binaries. When material from the companion star is drawn toward the neutron star, the magnetic field channels the accreted material into the polar regions of the star. This process produces intense beams of radiation that can be observed as X-rays, providing another method for studying the neutron star's properties. Understanding these compact objects is not just about observing X-ray emissions. The dynamic interactions between the accreting material and the compact objects offer a natural laboratory for testing our theories of gravity, general relativity, and quantum mechanics. For example, the intense gravitational pull near a black hole causes light to bend, creating an effect known as gravitational lensing. This bending of light distorts the view of distant stars and other objects, offering a rare opportunity to observe how gravity operates under extreme conditions. By studying the way in which light is bent near these systems, scientists can test Einstein's theory of general relativity in a regime where it has never been tested before. The rapid rotation of neutron stars also presents opportunities to test fundamental physics. As a neutron star spins, it emits radiation that can reveal important details about its internal structure. This radiation can be polarized, providing clues about the star's magnetic field and how it interacts with the surrounding environment. Additionally, the study of pulsars, neutron stars that emit regular bursts of radiation as they rotate, can help scientists better understand the state of matter at ultra-high densities. X-ray binaries are also important in the study of stellar evolution. These systems, which often involve a massive star in the process of transitioning to a compact object, provide valuable insight into the life cycle of stars. In particular, they give us a glimpse into the processes that govern the death of massive stars. When a massive star explodes as a supernova, it can leave behind a black hole or neutron star, depending on the mass of the star's core. By observing the evolution of X-ray binaries, we can learn more about the mass limits that determine whether a star will collapse into a neutron star or a black hole. This process of stellar death is not only important for understanding the fate of individual stars, but also for understanding the overall evolution of galaxies. The death of massive stars and the formation of compact objects like black holes and neutron stars can have far-reaching effects on their surrounding environments. In some cases, these processes can trigger the formation of new stars, while in other cases, the intense radiation and outflows from these compact objects can inhibit star formation. These feedback mechanisms play a crucial role in shaping the structure and evolution of galaxies. X-ray binaries can also provide important clues about the behavior of matter under extreme conditions. The temperatures and pressures within the accretion disks of these systems are so high that they can strip atoms of their electrons, creating a plasma state. This state of matter, which is distinct from the solid, liquid, and gaseous states we encounter on Earth, behaves in ways that are not fully understood. By studying the X-ray emissions from these systems, scientists can learn more about how matter behaves in the high-energy environments near compact objects. One of the most recent advancements in the study of X-ray binaries is the detection of gravitational waves. These ripples in space-time, first predicted by Einstein's theory of general relativity, are caused by the acceleration of massive objects. When two compact objects, such as black holes or neutron stars, merge, they create gravitational waves that can be detected on Earth. The detection of these waves has opened up a new way of studying the universe, allowing scientists to observe phenomena that were previously invisible. Gravitational waves from X-ray binaries provide a unique opportunity to study the properties of compact objects and the dynamics of binary systems in ways that are not possible through traditional electromagnetic observations. As technology continues to improve, the study of X-ray binaries will only become more sophisticated. The next generation of space-based telescopes, such as the James Webb Space Telescope and the Athena X-ray Observatory, will offer unprecedented views of X-ray binaries, allowing scientists to study these systems in more detail than ever before. These new observatories will also be crucial in the search for gravitational waves, providing new opportunities to detect and analyze these elusive signals. In the coming decades, we can expect to uncover even more mysteries about X-ray binaries and the fundamental forces of nature. Beyond the technical advancements, the study of X-ray binaries offers a broader philosophical perspective. As we learn more about these systems, we are reminded of the vastness and complexity of the universe. X-ray binaries, with their extreme environments and dynamic processes, offer a glimpse into the fundamental workings of the cosmos. They are a reminder that the universe is full of mysteries waiting to be uncovered, and that every new discovery opens the door to even more questions. The study of X-ray binaries is not just about observing distant objects in the sky. It is about understanding the forces and processes that govern the universe, from the formation of compact objects to the behavior of matter under extreme conditions. These systems are key to unlocking the secrets of the universe, and as our understanding deepens, we are likely to make even more astonishing discoveries that challenge our notions of space, time, and the very nature of reality. X-ray binaries, with their ability to offer insight into both stellar evolution and high-energy physics, represent a crucial intersection of multiple fields of study. Their complex nature enables them to serve as laboratories for a variety of astronomical phenomena, from accretion processes to relativistic jets. As astronomers and astrophysicists continue to probe the mysteries of these systems, the potential for groundbreaking discoveries is immense. We are on the precipice of an era in which the study of X-ray binaries could answer some of the most profound questions about the universe. To truly appreciate the significance of X-ray binaries, we must delve deeper into the unique characteristics that make them so compelling. One of the most intriguing features of these systems is their variability. The X-ray emission from these binaries is not constant but instead fluctuates over a range of timescales. Some systems exhibit rapid, almost chaotic fluctuations, while others show periodic patterns of variability. This variability can offer valuable clues about the physical processes occurring within the accretion disk and the inner regions of the compact object. The nature of the companion star in an X-ray binary also plays a vital role in shaping the system's overall behavior. In some cases, the companion is a massive, evolved star that is nearing the end of its life. As the companion star loses material to the black hole or neutron star, it experiences significant changes in its structure. The mass transfer rate from the companion to the compact object can influence the size and structure of the accretion disk, as well as the intensity of the X-ray emissions. Studying these changes allows scientists to gain a deeper understanding of how mass transfer works in extreme environments, and how it affects both the compact object and the companion star. Additionally, X-ray binaries can serve as tools for testing our understanding of the fundamental physics of accretion. The process by which matter is drawn toward a compact object is governed by complex physical laws, including gravity, magnetism, and radiation. In X-ray binaries, these forces interact in ways that are difficult to model, yet they offer a rich area of study. One of the key mysteries that scientists continue to investigate is the formation of relativistic jets. These jets, which are often associated with black holes, are streams of charged particles that are accelerated to nearly the speed of light. Understanding how these jets are formed, and why they are so energetic, is one of the primary goals in the study of X-ray binaries. The presence of these jets opens up a fascinating line of investigation into how energy is transferred within the system. Accretion itself is a highly inefficient process, with a significant portion of the energy released during the infall of matter being converted into radiation, particularly X-rays. However, some of this energy is also channeled into the relativistic jets. These jets are typically observed in systems containing black holes, but neutron stars can also generate jets, albeit under different conditions. The interplay between the accretion disk, the black hole or neutron star, and the jets offers scientists a unique opportunity to study how energy is released and transported in these extreme environments. Another critical area of study within X-ray binaries involves the way in which these systems emit radiation across the electromagnetic spectrum. While X-ray binaries are most well known for their X-ray emissions, these systems often emit across the entire electromagnetic spectrum, from radio waves to gamma rays. By studying the multi-wavelength emissions from X-ray binaries, scientists can create a more complete picture of the physical processes taking place. For example, the synchrotron radiation produced by high-energy particles in the jets can be observed at radio wavelengths, providing valuable information about the dynamics of the jets. Meanwhile, the high-energy X-ray emissions from the accretion disk provide direct evidence of the extreme conditions near the compact object. The role of magnetic fields in X-ray binaries cannot be understated. Both neutron stars and black holes possess powerful magnetic fields that can influence the behavior of the accretion disk and the materials surrounding the compact object. These magnetic fields are thought to play a key role in shaping the jets observed in these systems, with the interaction between the magnetic field and the accreting material resulting in the formation of highly collimated, relativistic jets. The study of these magnetic fields offers another avenue for understanding the behavior of matter in extreme gravitational and electromagnetic environments. Furthermore, the detection of X-ray binaries in other galaxies adds an exciting layer of complexity to the study of these systems. For years, X-ray binaries have been studied primarily within the Milky Way, where many of the closest and most well-studied examples are located. However, with the launch of more advanced telescopes and observatories, such as the Hubble Space Telescope and the Chandra X-ray Observatory, astronomers have been able to observe X-ray binaries in other galaxies. These distant systems, though much farther away, exhibit similar behaviors to those observed in the Milky Way, providing valuable insight into the broader distribution of compact objects in the universe. The study of these distant X-ray binaries allows scientists to probe the conditions of galaxies that are far removed from our own. By observing the emissions from these systems, astronomers can learn about the environments in which they formed and the conditions that govern the evolution of galaxies. Furthermore, these observations contribute to our understanding of the large-scale structure of the universe, helping to map the distribution of compact objects across different regions of space. The ongoing study of X-ray binaries also has implications for understanding the fate of our own Sunday. While our Sun is not massive enough to become a black hole or neutron star, the processes that occur in more massive stars have important lessons for the life cycle of all stars. The death of a massive star, whether through a supernova or some other mechanism, has a profound impact on its surrounding environment. The formation of compact objects such as black holes or neutron stars can influence star formation in nearby regions, and the energetic outflows from these objects can reshape their environments. Understanding these processes in the context of X-ray binaries can provide valuable insight into the ultimate fate of stars and their role in the broader cosmic cycle. Moreover, the study of X-ray binaries can provide a clearer picture of the early universe. The most massive stars, which are thought to form in the earliest stages of galaxy formation, are more likely to end their lives as black holes or neutron stars. By studying the characteristics of X-ray binaries in distant galaxies, scientists can learn more about the star formation processes that took place in the early universe. These observations could help us understand how the first black holes and neutron stars formed, and how they influenced the evolution of galaxies and the cosmic web. X-ray binaries are also important in the search for gravitational waves. As we mentioned earlier, the merger of compact objects like black holes or neutron stars generates ripples in spacetime that propagate across the universe. These gravitational waves carry information about the properties of the objects involved in the merger, and the dynamics of the event. The detection of gravitational waves has opened up a new frontier in astrophysics, allowing scientists to study events that were previously undetectable through electromagnetic radiation. By observing X-ray binaries and the gravitational waves they emit, scientists can gain a deeper understanding of the nature of compact objects and the fundamental forces that govern the universe. Looking to the future, the study of X-ray binaries will continue to evolve as new technological advancements allow for more detailed observations. With the upcoming launch of the James Webb Space Telescope and the European Space Agency's Athena X-ray Observatory, astronomers will have access to even more powerful tools to study these enigmatic systems. These next-generation telescopes will provide unprecedented views of X-ray binaries, enabling scientists to observe previously unseen details and answer questions that were once thought to be beyond our reach. In summary, X-ray binaries are among the most fascinating and dynamic systems in the universe. Their ability to provide insight into the nature of black holes, neutron stars, and the accretion process, as well as their potential to test fundamental physics and probe the early universe, makes them an essential area of study for astrophysicists. From their intense X-ray emissions to their potential to reveal the mysteries of gravitational waves, X-ray binaries offer an invaluable window into the universe's most extreme environments. As technology advances and our understanding deepens, we are likely to uncover even more secrets about these incredible systems, furthering our knowledge of the cosmos and the forces that shape it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.